Hello, and welcome to you all. Thank you for joining us at this webinar, IAG regional webinar. I'm Susan Conway. I'm going to be managing the meeting today. I am a research scientist in planetary geomorphology with the CNRS at the University of Nantes. I'm joined by Mauro Sodati, who is at the University of Modena and will be co-hosting this meeting, or will be chairing the second half. I should say that I am one of the vice presidents of the International Association of Geomorphologists, and Mauro is the president. We'd like to extend our thanks to the national scientific members of the IAG who enabled us to pull this webinar together, and those are the British Society for Geomorphology, the French Geomorphology Group, the Irish Geomorphology Group, and the Italian Association of Physical Geographers and Geomorphology. So this webinar aims to highlight some of the most, some of our bright and upcoming researchers in the field of geomorphology, and you'll see we have an exciting range of different geomorphological topics today. So thank you for joining us. Please feel free to join other webinars that are happening during this week. So this is the International Week of Geomorphology. This is the second year we've run this. So last year's one was kind of curtailed a bit by COVID, but this year we're taking advantage and meeting online instead. Just a couple of housekeeping notes before we get started. I'm going to try and keep myself to time here. How we're going to organize these talks, they're going to be 15-minute talks with 5 minutes at the end for questions. So if you want to ask a question, you've all noticed that you've all come in muted. That's intentional to stop background noise for our speakers. So what you have to do to get our attention is to raise your hand. And how you do that is you go down to the bottom of your screen and there's a reactions button. And in that reactions button, you can raise your hand. This will put you to the top of the list and we can then unmute you. The other option is if you don't have audio, or you think of a question while the speaker is speaking, you can actually leave that in the chat. So the chat again is activated down the bottom here, and it should bring up a window, sorry, that side of your Zoom. So I think I've covered all the necessary housekeeping notes. Mauro, if you confirm or not that I've done that. If you think of anything else quickly, otherwise we'll get on with the program.
Oh, I confirm that everything is fine, and I take the opportunity to say welcome to everybody.
Thank you.
Yes.
Good afternoon, everyone. Today, I will present the results of some studies focused on a recently deglaciated area of Mediterranean areas. The resettlement of glacier due to the climate change exposed a new patch of mountain land where new processes sunset. We can define this area as progression systems. Progression systems are defined by subtracting modern glacier outlines from little ice age outlines. So we consider that area in this presentation. As we can see from this picture, many surface processes acting in a very, very small portion of land with different magnitude and different time. And you can see slow processes, weather-related processes, periglacial processes. So we can define all these processes as a periglacial dynamic. No glacial processes that are directly conditioned by the presence of glacier. When we think of a proglacial system, the classical alpine proglacial system comes to mind. This is the case of one of the most beautiful proglacial area of the Alps, the Mortara Glacier proglacial system. These proglacial areas are characterized by a very large surface, up to 3 kilometers long, with very low terrain slopes, minus than 5 degrees, and a rapid biological colonization of the area. This is a typical study site, the Mortara Glacier, when along the the glacial area, you can find trees, you can find shrubs, and then herbaceous vegetation. But not all the glacial system are like that. In fact, the glacial environments are well studied in this area of the planet, like Alps, such as Arctic regions. But there are many other glacial systems that are where there are a lack of detailed studies, but are very, very important. In particular, here we consider the mid-low latitudes glacial area, in particular the areas located in the Mediterranean basin. From Morocco to Turkey, passing through Spain, France, Italy, and also Balkans, glacier and glacial area are present. So I will show you in the next slides the most interesting and the most peculiar ones. The southernmost Mediterranean glacial system is located in Morocco on High Atlas at about 4,000 meters above sea level. It's a very small glacial area. There is no active glacier yet today. And it's peculiar because the southernmost is closer to the Atlantic Ocean. Another very interesting glacial system is present in Spain. For example, this is the Picos de Europa, it is located in the northwest of Spain. Here we can find an active glacier, very, very small, that is smaller than 5 hectares, but during the littoral stage was higher than 0.05 square kilometer. This glacial system is very peculiar because it is also close to the Atlantic Ocean, with all the implications for the climate. We can, in Spain, the glacial system are also present in Sierra Nevada. You can see an active rock glacier located near La Veleta, is more than 300 meters above sea level. In this glacial circle, now there is not an active glacier, but there is an active rock glacier. And this is an evolution. The presence of rock glacier in glacial areas of Mediterranean is very, we can find it in different sites along the Mediterranean area. In Italy, we don't have only the Alps, a small glacier, and a very interesting glacial plain exists on the Apennines. This is the case of Caldera glacier, that now is fragmented in two distinct sectors. During the Little Ice Age, this glacier covered up to 0.1 square kilometers, so it's very important in dimension. It's a very important glacial system characterized by a very intense instability due to the climatic, topographic, and hydrological condition. The glacial area is located in a deep north-facing valley. That is a case of almost the totally of glacial areas in Mediterranean areas. We can find glacial system also in Balkans. This is the case of Pirin Mountains in Bulgaria, and even on Greece. This is Mount Olympus, that is the highest peak of Greece, which about 3,000 meters above sea level. And we find here a very small glacial system. No active glacier is present here today. But it's very interesting because in this system we can find littoral stage moraines close to close to younger Dias moraine and close to well-conserved late glacial maximum moraine. So in a very few square meters, we can find a very interesting deposition of moraine. I will show with this many situations, we can find that the Mediterranean production system are very different from the Alpine one. We in fact are located in high elevation sites, more than 300 meters above sea level, reaching up to 4,000 meters above sea level. And are very small, glacial system very small, with a very poor biological recolorization that is very important for the stability of the area. all these sites have a strong climatic control. Now let's take a closer look to the glacial areas of Turkey. In Turkey, glacialism is still present and widespread, and is important in two sites in particular, on Mount Ararat and on the Silo region on the Taurus Mountains. There are 51 ice bodies totally in Turkey, covering more than 12 square kilometers. The other three glaciarized sites of the Turkey are Munzur Mountains, the Eastern Black Sea Mountains, and the Monsufan, that are where only glaciers or snowfields are present today. I will show you two peculiar glaciarized areas of Turkey, in particular the Mount Ararat and the Taurus Mountains. Mount Ararat is a stratovolcano which achieves 5,000 meters of altitude. There is the only ice cap of the Middle East, and here we have conducted a scientific expedition in 2014 for investigate the glaciarized area of the mountain, but also the progressive system and the evolution of the ice here. Finding and mapping the characteristic of the area, we found, we investigate on the eastern flank of Mount Ararat a very peculiar landscape that is a 400 meters deep canyon. This canyon has a long history because several diarists reported calamitous events on 1840. But it's not clear how and when this event occurred and how is the nature of this event. These diarists report that this event obliterated several villages located at the foot of the volcano. They obviously obliterated also the proglacial system and the proglacial area of this volcano. At the end of the Aurora Gorge, we detect a very wide alluvial fan that have covered the present landform and also the basal flows. And we try to map the proglacial system of the area, but it's completely absent, completely obliterated from this event. We tried to figure out what happened in 1840. We find that the elongated landform that is present in the Aurora Gorge is not a landslide deposit, as before was reported from many travelers of the area, but is an ice body. In this picture, you can find some spots where ice emerge from the debris. A glacier in a not clear position, and combining this ground and data and the satellite data, we try to give an interpretation of this event that modify the area of Mount Ararat, but also strongly modified the area of Aurora Gorge. In 1840, a lateral volcanic emission generated a destructive pyroclastic flow. This was reported from local people, but also from some geological evidence, and a consequent rapid ice snow melt led to a density flow along this valley, along this the Aurora Gorge, which we interpret as lahar. After the lahar that destroy all the villages and all the landform presence, a rapid advance of a glacier occurred. We were in the last part of the little ice age, so the glacier can advance. But a glacier advancing in this valley that is characterized by the very high stability of slopes, the debris buried this ice body, so ice still exists now, buried from meters of debris. So it's a peculiar evolution, it's a sudden and extreme evolution of a glacial system. But in Turkey, there are much quieter glacial areas. So we look into consideration this area that is close to Uluduruk Tepe, that is one of the highest peak of Turkey, that is more than 4,000 meters above sea level, located between the boundaries of Iraq and Iran. This is the second glaciarized areas of Turkey, with 27 ice bodies covering only 3 square kilometers. So there are small ice bodies, but are very important because they are fundamental water resources in this area. The climate is arid or semi-arid, so during the summer, no precipitation occurs. So glaciers here are very fundamental for the water resource. We investigate this area through multi-temporal and high-resolution remote sensing approach using different platforms, Sentinel-2, Spot, Pleiades, or Corona. It's easy to work with remote sensing data here because the scarcity of vegetation maximizes the remote sensing potentiality, because all the area is evident from the space. And we have worked with images like this, that is Corona hexagon images, satellite data that have 58 years but are very.
You have 2 minutes.
I know. We mapped the area. Little Ice Age moraine ridge are well preserved now. We defined that 200 years ago, glacier covers 5 square kilometers. That is 50% more than the area currently covered by glacier. But these moraine are characterized by very intensive erosional processes. We note that widespread formation of glacial lakes occur in this area. It's covered about 0.1 square kilometers. The presence of glacial lakes is very important for the stability of this area. In fact, glacial lakes here, where there is no vegetation, there is no herbaceous vegetation, glacial lakes have a stabilizing function. They slow down the flow of meltwater, trapping sediments. Here we can find ice marginal glacial lakes, and we note that the moraine ridge is completely stable, is completely not eroded. Here, otherwise, we note how, in absence of glacial lakes, there is more intensive linear erosion. So where there are no vegetation, the glacial lakes are very important for the stabilization of the glacial areas. The lack of stabilizing factor in this area causing diverse surface processes that active simultaneously. Here we can find an example where we have mapped the glacial deposit, but the glacial system is characterized by many processes that occur in the same time, as slope processes, as erosion. So the paraglacial dynamic of this area is very, very important, in particular where there is no vegetation that stabilizes the paraglacial system. So moving to conclusion, the Mediterranean glacial system have a strong climatic control. It is very important to investigate and to analyze the role of paraglacial processes, because many factors acting simultaneously. It's important in the absence of the stabilizing function of biological colonization, the stabilizing function given by proglacial lakes. Now the works will continue. I wish thank you for the attention. In particularly, I will thank my co-authors. Thank you very much.
So good afternoon, everybody. So I'm Florence Magnin, and I come from the EDITIME laboratory that belongs to the CNRS and the Université Savoie-Mont-Blanc. And today I will present you the work that we conduct with my colleagues about rockwall permafrost modeling that we developed to better understand periglacial rock slope failures. And I will start with introducing you the research context, which stems from the increasing destabilization in high mountains or in the Arctic. So rockwall destabilization with various impacts. So for example, in the Mont Blanc Massif, there are very frequent small magnitude rockfalls that are impacting mountaineering practices or professional guiding activities, for example. And there are also some higher magnitude events such as rock avalanches that may trigger chain reaction processes, such as the example you see here, one in Switzerland and one in Greenland, that have triggered either debris flow or tsunamis. And the last one, which is very recent and that I guess you may have heard about, is the Chamoli rock ice avalanche that occurred in India this February, and that caused a huge flood down in the valley. So among the various processes that may be responsible for this increasing rock slope destabilization, permafrost is thought to be the main responsible parameter because it directly reacts to atmospheric warming and because it interacts with many other rock slope stability parameters. And one evidence of the role of permafrost in this rockfalls or rock avalanche is the presence of ice in rockfall scars that is very frequent. And we do not only observe ice, but we also observe water sometimes. And we know that permafrost strongly interacts with hydrology. For example, the ice in rock wall fractures may seal the fracture and cause then perched water table that could lead then to high hydrostatic pressures and possibly leading to rockfall. So there are various hypotheses that link rockfalls or rock avalanches to permafrost dynamics. The oldest one is based on laboratory experiments that have shown that that ice field fractures lose in resistance when they warm towards 0 degrees Celsius. So this is here the factor of safety of a rock ice sandwich that is warmed in a laboratory. And we see here that below or above, minus 1.5 degrees Celsius, this is becoming critically unstable. Then this ice field fracture, they might be altered either by the slow heat conduction from the surface to depth or by enhanced warming caused by water infiltration in the fractures. And the second hypothesis is, as I said, that this water infiltration then can also create high hydrostatic pressures. So to work on this hypothesis, we have conducted various investigations with my colleagues since about a decade now. My colleague Ludovic Ravanel has, for example, invented rockfalls in the Mont Blanc Massif, and he has shown that there is a clear relationship between hot periods, as much hot summer as hot decades, and with rockfall frequency. Then on my side, I have developed transient thermal models that I have applied to various sites. Here's an example of the thermal model on the top part of the Aiguille du Midi here, which is crossing with a profile that is crossing a temperature borehole that we have equipped in 2010. And with this model, we can show that rockwall permafrost has strongly degraded over the past 3 decades first, and that these models are suitable to reproduce temperature evolution at a depth of 8 meters and deeper. In the shallow layer here, you have the comparison of measured and model temperature. Here is the measured and model temperature for this borehole, for example. Below 8 meter depth is quite reliable, and above meter depth, like in shallower depth, there are various processes such as air, ventilation in the fractures, or water infiltration in the fractures that may cause discrepancy between modeled and measured temperature. So now we try to build upon these accomplishments, and this is what I will present you today. So with this inventory of rockfalls, we try to determine whether there is a statistical relationship between rockwall temperature and rockfall occurrence. And with this transient thermal model, we try also to incorporate hydrological processes to determine the role in permafrost dynamics. So I will first start with presenting you this statistical analysis. So for this analysis, we have used 209 rockfall events that are mapped here. Those are the green dots. They overlay a map of mean annual rock surface temperature that was created much earlier, and that is representative of the steady temperature for the period 1961 to 1990. And for all these rockfalls, so we knew the mean annual rock surface temperature, we knew the exact location of detachment, we knew also the date of occurrence and the depth of the detachment. So for all these rockfalls, we simulate the temperature dynamic prior to failure. So we use the mean annual rock surface temperature to create a rock surface temperature time series since the early 1990s. So we just apply to this mean annual rock surface temperature, we apply the air temperature anomaly or day-to-day change registered in Chamonix, which means that we assume that the rock surface temperature strictly follows the air temperature change. And with this data, we forced a transient thermal model, which is in one dimension, that we forced at the bottom with a correction heat flux. So for you to understand this heat flux is, let's say that this is the rockfall location, if you see the mouse, and the temperature at depth is controlled by the heat fluxes coming from the various surrounding rock faces. So we calculate all these heat fluxes, and then we constrain the temperature at the bottom. So the approach is a bit complex, but what you have to keep in mind is that for each rockfall, we simulate such temperature profile. So this is the surface, and this is about 30-meter depth, and this is the early 1990s, and this is the present time. So we simulate temperature dynamics for all rockfall. And let's say now that this is the day of rockfall events. So for each rockfall, then we look at the surface temperature and at the scar temperature at the day of failure. And we also look at the surface temperature and scar temperature percentile, which means that we try to determine how high is this temperature compared to the temperature time series before. And we look at these temperature variables for the day of rockfall and up to 2 months before to have an idea of how the temperature has changed prior to failure. Then we do this simulation for each rockfalls, but only for a bunch of random events. So for each rockfall, we determine 1,000 events randomly. So we picked up some dates, basically at the approximate date of failure. So most failure occur between June and October. So we picked up 1,000 dates between June and October over this entire time series to compare them to the result of the real rockfalls. So we do this with the random events just to determine the statistical significance of our results. So it's just to say if we could have found the same result with the random events as the one that we found with the real events. So now we'll present. Now we'll present you the result briefly. So this is the scar temperature when we for all rockfalls, and this is the scar depth. And this is 1 day prior to failure. So what we see is that most rockfalls that are shallower than 4-meter depth, they occurred in positive temperature, while those that occurred at a depth greater than 4 meters, they occurred in close to 0 degrees Celsius temperature. And surface temperature was always positive, mostly positive, whatever the scar depth. So what we can say from that is that permafrost-related rockfalls, so rockfalls that occur in negative temperature, may only concern events that occur at depth greater than 6 meters. And most events that are shallower than 4 meters, they are not related to permafrost. Then if we look at the scar temperature percentile, so this is the real value and this is the random event. So back to this figure, you see that we have similar pattern, but here the pattern is very different. We see that the real events are significantly higher percentage, so this means that they are significantly warmer than the random event. Whatever, like we look at the scar temperature or surface temperature is the same. So what we can say from those results is that extraordinary high temperature is a common triggering factor for both frozen, like those deeper rockfalls, and non-frozen rockfalls, those that occur at shallower depth. They all occurred under extraordinary high temperature at the surface and at depth of failure. So then we perform a test to determine the statistical significance of a result. So it's a Kolmogorov-Smirnov test, which basically compare the distribution of the real event with the random events. With this test, we determine a critical value. above which all results are significant, which means that what we found for the real event is significantly different than what we found for the random event. And this is the result of the test. So this red line is the critical value. Everything that is above is statistically significant, and below we cannot really say if it's significant or not. So what we learned from that is that here it is the average surface temperature for a different averaging period before failure. And surface temperatures is always, in average, significantly warmer than usual when the rockfall occurred, and especially 1.5 months before the event, and also 1 to 5 days before the event. And this is a kind of, this is in relation with the scar depth temperature, which is here, which is particularly significantly high at the day of rockfall and up to 3 weeks before. So what we can say from that is that the hot periods that last at least 1.5 months and that are combined with 1 to 5 day hot spell, they are particularly prone to rockfalls. And finally, we can say from that curves that rockfall are a direct reaction to extraordinarily high temperature. Then when we consider the uncertainty boundaries of our model, this is less significant. So we should work on that. So with such work, with such statistic, we can then claim that we could support the development of a rockfall susceptibility index based on weather forecast or air temperature forecast. Now I will briefly introduce the other modeling approach, which is the coupling of thermal and hydrological processes. So compared to thermal model, when I was only considering the top part of the degree d'humidity, here we have to consider the entire rock face because we have to account for realistic water table. And here's a non-perennial lake that is somehow the outlet of this water table. So we just set up this water table by running various trial and error simulation until we find a steady water table. Then we draw the main fractures that we found on the site. So we didn't try to be realistic with the fractures. Not in terms of aperture or density, but we just try to draw a few fractures that will represent the preferential flow path for water. And then we simulate heat and water transport using the Darcy law. Then we run the simulation for various case studies. One is saturated without water flow, and this is what we were doing until now. Then a second one is non-saturated, unsaturated without water flow. And we see that after initialization, when we run the model with positive temperature for many years, we have the same temperature pattern. But for our third case, which is saturated with forced water flow into the fractures, we have a different temperature pattern. We see that the water drags the code from top to bottom, and it is colder at depth. Then when we steadily freeze the rock mass, so we create the permafrost body, we have a greater permafrost or deeper permafrost body when there are water flows, because still the water drags the code from top to bottom. And finally, when we steadily freeze the rock mass, when we steadily thaw the rock mass, so we run then positive temperature at the surface. It takes longer to thaw here because the permafrost body is more deep, but it's locally thaws much quicker. Like here, we have a thawing wedge that is delineated by fractures. And we run for this to understand a bit better a fourth case study, which is unsaturated except the fractures. Here we force water flow in the fractures, so it's the same as this one, but we then force water flow in fractures when it thaws. And we do not have this thawing wedge, but we have thawing corridors. So what we learned from that is that water flows into rockfall fractures, they strongly affect the freezing and thawing pattern. They create greater temperature gradients and they enhance thawing, especially in saturated fracture and rock mass. And then I just present you an outlook. With this model, we can then image pressure fields, hydrostatic pressure fields. So when it's saturated, it's very complex pressure fields. When it's unsaturated, except in fractures, it's less complex. But what we are interested in is that for all cases, we reach easily values greater than 100 kilopascal, which is, according to very last modeling studies, a critical value to trigger rockfall at the perch water table in rockfall permafrost. So with such model, we can then build up a complete thermo-hydromechanical model using this model output. So to conclude, there is a need for a better understanding of periglacial rock slope destabilization processes in order to support alpine and Arctic communities in their adaptation strategy to a changing cryosphere. And to answer that need, we have conducted statistical analysis of rockfall temperature and rockfall occurrence. We have made some first steps toward the determination of rockfall susceptibility index. And we also tried to develop more complex model by incorporating hydrological processes in permafrost dynamics. So I have a thank you slide, but I think I will leave it this way. Then you can also have a look at the conclusion, and I take questions if there are any. Thank you.
Great. Okay, so I'm Helen, and I've just started as a postdoc at Trinity College Dublin. And today I'm going to be talking through a little bit of my PhD research and talking about understanding the resistance of UK salt marsh substrates to erosion. So why do we want to understand marsh resistance to erosion? So marshes provide a wide variety of ecosystem services, from habitat provision to pollutant storage, and they also protect us from flooding and erosion. So understanding the resistance of these substrates on our shores is really important because we know that marshes are actually retreating in many locations from their seaward edge. So knowing why this retreat is occurring in some places and not others is really important if we want to understand how the provision of these ecosystem services is going to change in the future. So this work focused on 2 sites within the UK. So one in the northwest of England called Warton Marsh, and that's on the left there. And it's an open coast marsh, which basically means it's not behind any kind of barriers or within an estuary, which means it's directly exposed to waves and currents. It's composed of coarser sediment than our other sites, so it's silt and sand dominated, and it's also grazed by sheep. We've got another site in the southeast of England in Essex called Tillingham Marsh. This is also an open coast marsh, but it's much finer sediment, so it's silt clay dominated. So I hope you can see that in the photos there, but it's also ungrazed. And we can see from the vegetation that the vegetation at Tillingham is quite floristically diverse, but at Warton, it looks much more like a grass. So it's dominated by a species called Puccinellia maritima. So there's quite a difference there in the vegetation types that we see. So just to give you some photos of the sites and a bit of an idea of the geomorphology. So at the top, we can see photos of marsh creeks at each site, and these are a key part of the drainage structure of salt marshes. So on the left, we've got Warton Marsh, and we can see that the creek is a lot wider, and there's kind of slumping of blocks into the creek there. At Tillingham on the right-hand side, we can see the creek is much narrower, and there's evidence of some small desiccation cracks on the side there. Now at the bottom, we've got photos of the marsh edge at each site. So at Warton, we can see that there's this cliffed marsh edge, and that's about 1 to 2 meters high along the edge of the marsh, with blocks in front of it that have failed from the cliff. And then also we can see this stripping of the vegetation back from the marsh surface. Now at Tillingham, we have these very different formations. They're called ridge and runnel features, and they are higher as you get closer to the marsh. So this is looking out over the tidal flat. So in terms of my sampling strategy, we wanted to look at 4 sites at each marsh to try and encompass the range of environments we get at within a given marsh, because we wanted to compare the within site variation in substrate composition to the between site variation in substrate composition. So we chose a tidal flat site, a marsh edge site, a creek edge site, and an inner marsh site. We took lots of bulk samples, and these were used to measure composition. So these were taken at 10 centimetre depth intervals, down to 60 centimetres depth at the marsh edge, and down to 30 centimetres depth at the other sites. We also took shear strength measurements, which were used to give an idea of the substrate resistance to erosion. And this was done using 2 methods, which I'll talk about a little bit later, but a cohesive strength meter and also a shear vane. And these measurements were again taken at 10 centimetres depth, but this time until we reached the water table, because the water table can interfere with what we're measuring. And we took replicates at each site, well, at each sampling location. So for the shear vane, we took 10 replicates at each sampling location. And for the CSM, the cohesive strength meter, we took 3 replicates at each sampling location because it's a bit more time consuming. So in terms of the methods for understanding the substrate composition, this was based on the bulk samples which were taken to the lab, and we used loss and ignition based on the British Standards technique, the protocol, and this was used to measure the water content, the organic content and the carbonate content of the substrate. We also measured the root mass as a percentage of the dry mass, and this was basically done by wet sieving the sample at 425 microns and drying it overnight, or for many nights in most cases. We measured the particle density, so that's the density of the individual solid particles, and again this followed British standards. And then finally we measured the particle size distribution, and not only looked at the actual particle size distribution, but came up with, used some values to kind of describe the grading or the variation in particle size that we see. So that's the uniformity coefficient and the coefficient of curvature. So you can see on the right here my particle size results. So we can see in blue we've got the Tillingham results. So we've got a much finer grain size here, but a platykurtic to mesokurtic distribution. With the Wharton measurements, we can see a coarser grain size, but with a much more leptokurtic distribution. So I'm going to talk you through some of my results here, and I'm afraid I've had to remove the scale on the graphs just because it's unpublished data, but it's the overall trends that are important here. So we can see here Tillingham's on the left of each graph and Wharton's on the right of each graph. We can see that the moisture content, the loss and ignition and the carbonate content were all higher at Tillingham than at Wharton, and the loss and ignition is a proxy for organic content. We can see there's quite a distinct difference between the two sites here. So for example, the moisture content might reflect differences in inundation regimes, precipitation patterns, but also drainage within the site. And we can see that, so this is the particle density and the root mass results. And again, we can see that both particle density and root mass were higher at Tillingham than at Wharton. And the particle density likely refers to the kind of the composition of the particles, so the minerals that we've got present. But the root mass was more variable at Tillingham as well, and this links back in quite nicely with the fact that we saw that the marsh canopy was floristically diverse at Tillingham, whereas at Wharton we've just got this fairly monospecific coverage, and that's probably why we see more variation at Tillingham. So then measuring the substrate shear strength. So I mentioned that we used a cohesive strength meter and a shear vane. So the cohesive strength meter is shown at the top right here, and basically this grey chamber here is placed on the sediment. It's filled with water, and then we fire a jet at the surface. We measure the change in turbidity of the water within that chamber over time, and when the turbidity reaches a critical threshold, we can equate that to the erosion threshold of the sediment. The shear vane on the bottom right, essentially this is a rod with paddles on the end, which we push vertically into the sediment. We twist it, and there'll come a point when the sediment fails. We can then measure the torque which was applied when the sediment fails, and this gives us an approximation of the undrained shear strength. So for the erosion threshold, again, we can see, so the erosion threshold was much higher at Tillingham than it was at Wharton, and it was more variable at Tillingham as well. Now, this is really interesting because this actually contrasted with the results we got from the shear vane data. So when we move on to the shear vane data, we can see that the undrained shear strength at Wharton was much higher than it was at Tillingham. So we started to think about some key questions that these results were showing. So we were wondering why the veins and the CSM produce contrasting results, and also how the shear strength of the substrates, as measured using both of these methods, might be affected by substrate composition. So we started to think about what the vein and the CSM actually measure. So on the left here, we've got a 2D schematic of the vein. The apparatus is pushed vertically into the sediment, twisted, and the torque at which the substrate fails is recorded. So this most likely reflects a bulk failure process. And it's important to note here that the 3D footprint of the vein is a lot larger than that of the CSM. So the force is being applied over the whole area of the paddles. And for the CSM, the chamber is placed on the sediment. So this kind of box that I've drawn here approximates that chamber. It's filled with water, and we measure the change in turbidity over time as we fire a jet. And as you can expect, the pressure is highest in the center of the chamber there. And this likely reflects more of a kind of grain by grain erosion or entrainment of sediment particles process. So given that these two methods of measuring substrate resistance to erosion seem to measure two different erosion processes, so the bulk failure and the grain by grain erosion, it's likely that they're affected to different extents by various aspects of substrate composition. So we started to test this theory by using multiple linear regression to see if the shear strength measured by the veins or the CSM could be related to various different aspects of substrate composition. So we used all the measures of substrate composition from earlier, and we produced a list of all statistically significant models. So you can see them here. Now, the main thing just to note is actually that you can see from the veins here that they're affected by a mixture of minerogenic and organic components of the substrate, whereas the CSM here is affected by pretty much only the minerogenic substrate component. And this is really important when we start to think about the kind of erosion processes which are occurring at the marsh edge, and also the speed at which retreat might occur. So then we started to try and link in these results to the rate of retreat at the marshes. So we mapped marsh edge retreat over a 24-year period at Tillingham and a 15-year period at Wharton. So we used aerial imagery at Tillingham, so aerial photographs, and at Wharton we had to use LiDAR because the availability of aerial imagery wasn't very good, but we ground truthed this and we checked, and because it's got this quite high cliff at Wharton, actually the LiDAR was really quite good enough for our purposes. And we used a software called Amber to extract key parameters on the marsh edge position, and it tells you things like retreat rate per year and how much it's retreated over the whole time period. We can see the sampling locations in the red dots on each of these maps, and the Amber code was run over these areas in the box, and that was about a 250 metre section at each site. But we could see some quite considerable differences in the rate of retreat at the two sites. So while Tillingham over the period, the monitoring period, was retreating by about 30 centimetres a year, the area at Wharton was actually retreating by about 13 metres per year, which is really quite substantial and obviously has quite considerable impacts down the line in terms of the ecosystem services, especially if we're planning in terms of habitat provision and that kind of thing. So this next bit is a little bit more qualitative, and it's based on inference from field photos, but it provides an initial attempt at linking the methodological results we found earlier, so that the vein and the CSM measure different erosion processes, with the rates of retreat at the marsh edge and what we can actually see in the field. And it also starts to form an idea of what future work might want to focus on. So we've got this photo of the cliff edge at Wharton at the top right here, and we can see that this cliff edge is fronted by blocks. So these blocks are evidence of bulk failure. They tend to be failed blocks which haven't yet been removed by the waves or the currents. But we know that grain by grain erosion likely also occurs. And this is particularly because the resistance to the grain by grain erosion was low, and we know that the cliff edge is impacted by hydrodynamic forcing. So here the grain by grain erosion was low, but the resistance to bulk failure was really quite high. So given the fact that we see this rapid retreat rate at Wharton, this implies that the low resistance to grain by grain erosion might actually be setting the pace of block failure, and therefore might be setting the pace of retreat of the marsh. At Tillingham in the bottom right, on the other hand, we have this ridge run-on margin morphology. And here there's very little evidence of bulk failure processes. So the resistance, but here we found, that there was very little resistance to bulk failure processes, but at the same time, there was a very high resistance to flow-induced erosion as measured by the CSM. And here the retreat rate was quite slow, so we can start to say that maybe the resistance to flow-induced erosion here, which was high, is one of the main influences on the retreat rate of this marsh.
2 minutes.
Thank you. So we found that the resistance to flow-induced erosion at both of these sites, at least, controls retreat. And because of this, and we found that the flow-induced erosion largely depends on particle size parameters, we're now starting to see that characterizing these particle size and grading parameters is probably quite key for understanding the retreat rate. And this can be done in conjunction with understanding the marsh edge morphology, which can give us an idea of the erosion processes. So in summary, we found that the veins and the CSM measure different erosion processes, and therefore they're influenced by different aspects of substrate composition at the two sites. Veins are affected by both minerogenic and organic properties, largely because of that 3D footprint that it has, and it comes into contact with all of the different material in the substrate, whereas the CSM is affected mainly by minerogenic properties. And this is really key for understanding how the ecosystem services that are provided might change in the future. So future work needs to start to understand the relationship between the marsh margin morphology, the dominant erosion processes and rates, and also the substrate composition in order to forecast future change to marsh aerial footprints. Thank you.
Perfect. Hi, welcome from Italy, and many thanks for having invited me to share this great event. My name is Chiara Martinello, and I'm a PhD student at the Department of Earth and Marine Sciences of the University of Palermo. My research project is focused on landslide susceptibility modeling under extreme event-driven triggering, including experimental areas in the Italian Apennine and Central America, mainly El Salvador, Guatemala, and Honduras. The issue that I'm going to share with you is about the limit and critical aspect in applying storm-triggered debris flow susceptibility modeling in Central America. Okay. First of all, a few introductory concepts about debris flow susceptibility. A debris flow is a rapid mass movement in which a combination of loose soil, organic matter, rock, water, and air mobilize as a slurry that flow down slope. Commonly, this type of phenomena are triggered by intense surface water flow, as well as from other types of landslides. Generally, debris flows canalize into channels, enriching in water and entraining very variably sized debris. So high accumulated debris and very far and fast propagation typically results in potentially very destructive phenomena. And the first step to cope with this is recognizing the source area. Okay. Landslides arise as interaction between a trigger and the local environmental conditions. Considering the preparatory causes as stable over time, we can statistically model the relationships between a known past landslide scenario and the known environmental conditions for predicting future landslide scenario, exploiting the rule stating that the past is the key for the future. This means evaluating the landslide susceptibility assessment for a specific area and a specific trigger. But which kind of trigger? In my research, I'm focused on rainfall trigger. This type of trigger can be normal or extreme, the latter being characterized by high intensity with a great deal of rainfall in a short time. Here, I focused my presentation on three main points. Sorry, one moment. Oh, sorry. I need to, okay. The first, can landslide susceptibility assessment evaluated by normal trigger be useful for landslide scenario caused by an extreme trigger? The second, to what extent do the relationships between preparatory causes and the trigger events depend on the trigger intensity, which would hamper the predictive power of a landslide susceptibility model? And at the same time, can the relationships between landslide scenario and environmental conditions be exported to similar areas? To explore these issues, I'm focusing on some volcanic areas in El Salvador. Due to its geographical position, El Salvador is frequently affected by hurricanes, which are responsible of wide landslide triggering, affecting the very steep slopes where pseudo-coherent lithologies largely outcrop. Okay. For the first issue, a 26 square kilometer wide basin northeast of the Ilopango Caldera was studied. Using Google Earth images, we prepared two debris flows inventories, a 2003 inventory, which is related to the normal rain season, with landslide are diffused, especially along the very steep slopes, and the 2009 inventory, which is related to the extreme rain of Ida hurricane, whose triggered landslides are widely present throughout the area. All the landslides were mapped by a polygon and identified through a landslide identification point. In fact, in a number of studies, we have verified that these head source sector very effectively represent the activation condition for surface debris flow. Land use and elevation were used as predictors, while furthermore, by using GIS software, the following then derived predictors were obtained: the steepness, aspect, profile, and plan curvature, stream power index, landform classification, topographic erogeny index, and topographic wetness index. The 10-meter pixel structure of the source dam was adopted for partitioning the study area into mapping units. About the model building strategy, self-validation and chrono-validation schemes were employed to evaluate the performance of the model. Through a random splitting of the same landslides inventories, SELF 2003 and SELF 2009 model were validated, while chrono-validations were employed to evaluate the skill in predicting the 2009 landslides locations for the forward model and the 2003 landslide scenario for the backward model. So for SELF 2003 model, an excellent AUC value and good sensitivity and specificity were obtained, suggesting a general good performance of the model. SELF 2003 model show an excellent AUC value with an excellent sensitivity, but a limited specificity. As expected, the forward model shows that the landslide scenario linked to the normal event is less performing in predicting the extreme landslide scenario, and the backward model suggests that by using calibrating with an extreme landslide scenario, the normal event is correctly predicted, as well as the self-model, and potentially unstable cases areas were detected. Please, for other results and analysis, consider this paper. For the second issue, 4 volcanic areas were studied where landslide scenario linked to extreme events were recognized. In particular, for the Ilopango Caldera and San Vicente volcano, debris flow triggered by the Ida hurricane were detected, while for the Coatepeque area and San Salvador volcano, ones produced by the 12E. The 12E is a tropical depression that occurred in October 2011. Okay, self-validation procedures were employed to evaluate the performance of the models, and then spatial validation schemes were employed to evaluate the skill in predicting the Ida landslide scenario of the Ilopango caldera by using the relationships obtained with the 12E landslide scenario of Coatepeque area and vice versa. Moreover, by putting together all the archives, a total model was performed and validated. Okay. The results show very good performance for all the self-validated models. The AUC values are between good and excellent, and while general limited specificity arises. It is worth to note that the number of unstable cases with respect to the total area is very low. In fact, generally the models propose a huge number of positive cases, actually classified as false positives, which could later the searched future positives. Partial validation results are just satisfactory for the Ilopango to Coatepec test, while the Coatepec to Ilopango transfer is not acceptable. In fact, while the relationships between the IDA landslide scenario and the predictors seems to work in predicting the 12E landslide scenario, the opposite is not true. These results seem to suggest that the landslide scenario linked to the two extreme events are different, with more landslide activated by the more intense event, the hurricane, which take to extremes the relationships. Finally, excellent results arise when the total model is employed. The AUC value of 0.87 is very high, and the sensitivity shows that 83% of unstable cases is correctly predicted, and at the same time, a reasonable number of false positives is produced. The most important variable of this model are some classes of lithology, slope, elevation, and some classes of land use and landform classification. And these classes are also the most affected by the landslides. In particular, for the geomechanical units, the class 5 and 7 corresponding to the soft and medium soil are the most affected. About the land use is the permanent crops class, the most affected. And finally, for the landform classification is the class 5 corresponding to the open slopes. Okay, in taking the final conclusion of this test, in light of some critical steps such as the diagnostic area and mapping unit partition, it is very worth to note that all the model and the related map can be assumed as geomorphologically sound, allowing to obtain a quantitative estimation of landslide susceptibility well rooted on the expected morphodynamic model for the debris flow activation. In particular, the first test proves that a landslide scenario linked to a normal event cannot be useful to evaluate to detect the relationships between an extreme landslide scenario and the predictors. On the other hand, with the extreme landslide scenario, it is possible to predict the most of the phenomena linked to the normal event. Okay, with the second test, another spatial validation was tested. The two areas are very similar, study areas are very similar.
2 minutes.
Yes. Are very similar, but each landslide scenario was produced by a different extreme trigger. This test seems to suggest that several extreme triggers produce several relationships, but by using the landslide scenario linked to the more intense event, the most of the phenomena is correctly predicted. And finally, by putting together all the archive, the total model was produced, and as confirmed by the results, and as confirmed by the results, this method seems to be the most performing. Therefore, analyze at the same time several landslide scenarios linked to different extreme triggers seem to be the most approach to evaluate the susceptibility, the landslide susceptibility. Thank you.
Hello, my name is Pauline Letortu. I'm lecturer at the University of Western Brittany. It's an honor to present my research on cliff erosion and coastal flooding hazard. But as you know, research is collective, so I would like to mention some colleagues with whom I work: Emmanuel Augereau, Stéphane Costa, Robert Davidson, Christophe Delacour, Niki Velpidou, etc. So I completed my PhD thesis in coastal geomorphology in 2013. I was hired as a lecturer in 2014 in the LETG lab, which means Coast, Environment, Remote Sensing and Geomatics. I work on coastal hazard, erosion, coastal flooding, and especially the erosion of the coastal cliffs, which have long been neglected in research, whereas cliffs exist on roughly 52% of the global shoreline. My main research question is how to better understand coastal hazards, especially cliff erosion, in order to improve the risk management. My talk will be divided in 3 parts. So first, I practice multidisciplinary approach through the concept of systemic vulnerability. Many territories are exposed to risk. Risk is a combination of hazards and stakes. Hazards are more or less natural processes likely to damage or destroy the stakes that are exposed to them. Stakes are what we risk losing: people, infrastructure. In these areas, there is a high knowledge demand from coastal managers and elected officials to improve practices and strategies for managing coastal risks. Because the traditional approach of the risks is not sufficient to integrate all dimensions that influence risk and its management, the concept of systemic vulnerability emerged to assess the capacity of society to respond to potential crises in terms of adaptation and resilience. This concept, created by Derkel, encompasses 4 components: hazard, stakes, management, representation, using a multidisciplinary approach. Management encompasses means by which risks are managed and their application by the actors involved in governance at the field level. Representations reflect the relationship that people living in the region have with risk, relationship to place, risk sensitivity. This component has long been neglected in risk studies. In the OSI-RISK project, initially founded by the Foundation of France, we are geographers, geoscientists, economists, psychologists, computer scientists, and stakeholders to deploy methods and tools to integrate the concomitant evolution of hazards, stakes, management measures, and representation in order to follow the vulnerability trajectories of territories. It enables the components that contribute the most to the systemic vulnerability to be identified and thus modified by relevant actions. This project was first deployed in 4 pilot sites in Normandy and in Brittany, and is currently deployed in the Department of Finistère thanks to its financial support. To monitor the evolution of each component, we use indicators defined by scientists and stakeholders. For example, for the hazard component that I coordinate, there are 5 included eroded distance per year per 100 linear meters for the erosion hazards. Indicator measurements are done thanks to standardized protocols. Indicators of the component are then integrated to an index per component and to other components in order to have the systemic vulnerability to coastal risk. Each step, indicators, indexes, is viewable thanks to a free web GIS called OSI, and that could be a great tool for dissemination, but also for management decision. I also practice multidisciplinary approach through the cliff instrumentation. A location and time of cliff failure remain unpredictable due to an incomplete understanding of cliff fatigue and cliff failure mechanisms. The cliff failure results from the interaction of both internal factors, rock strength, structure, and external factors. The external factors include continental, precipitation, temperature, marine, tide, and anthropogenic phenomena, for example, coastal defense structures that modified the sediment budget. A few studies have collected a database combining a precise record of cliff failure events and the associated forcing factors, which would allow the assessment of the respective contribution of the erosion processes. However, even with a database, unraveling the contribution of the factors is difficult, partly because there is a variable time lag between the forcing signature and the failure event, complicating the identification of correlations. Within the F3 project, I coordinated with Katia Lotte and Nicolas Ledantec, and within the Ricochet project, ambitious, continuous, and multi-parameters instrumentation experiments were set up at a gneiss cliff in Plougonvelin in Brittany, that you can see on the slide, and in a chalk cliff in Sainte-Marguerite-sur-Mer in Normandy for 13 months. The aim with our monitoring is, for example, in Normandy, we have monitor key environmental parameters, both on a cliff top or on a cliff face, precipitation, tide, and internally, water table, temperature, and also key cliff behavior parameters, cliff top promotion, deformation, possible failure events, in order to improve knowledge of the respective contribution of internal and external factors responsible for cliff fatigue and failure. The biggest challenges to these ambitious instrumentation experiments are to process all the data and to combine them in order to use a multidisciplinary approach. This work has not been achieved yet, especially for geophone data analysis. One of our first results in the Ricochet project in Normandy is about the analysis of extensometers and environmental conditions. Thanks to statistical analysis, we identify 4 types of environmental conditions that can be identified as responsible or not for the displacement on existing fractures. High significant wave height, high groundwater level, and high tide level constitute the preferred situation for displacement, both in frequency and in intensity of displacement. Low significant wave height, low water table level, low tide level constitute the least favorable condition for displacement with low frequency and intensity of displacement. Future collaboration with Canadian colleagues is planned for 2022 in order to transpose a part of our instrumentation there. The aims are to make progress in data analysis together and to compare results between both sides. Another emerging field of my research on coastal cliffs is the potential of oblique satellite imagery to monitor cliff erosion. To observe all the changing of the coastal cliff, the needing data are 3D data of the cliff face from the cliff foot to the cliff top, which is the best proxy to observe all erosion events at very high spatial resolution and very high temporal frequency and over large areas superior to 10 kilometers in order to observe information on the hydrosedimentary cell scale for relevant coastal management. Methods have existed since the 2000s to monitor cliff face erosion, for example, terrestrial laser scanner. But these methods are demanding in terms of people on the field and with a spatial, a limited spatial representativeness of the data. Since the launch of the Pleiad satellites in 2011 and 2012, it has been possible to access spatial imagery with a resolution of 0.7 meter at nadir, with a daily revisit, with a swath of 20 kilometers, and with an oblique view up to 47 degrees, making it possible to observe the cliff face in a new way and at preferential price for research. Thanks to the financial support of the CNES, the French Space Agency, I coordinated the Aerophalite project to assess the potential of oblique and very high-resolution Pleiad images for the 3D reconstruction of the cliff face and thus the monitoring of erosion. To do that, we tested our approach along the tall cliff around Dieppe in Normandy, where we had ground truth data, but it was a really challenging site for spatial imagery due to its northern orientation, the shading on the cliff face, and often disturbed weather conditions. But if it works here, it will work anywhere. So thanks to free processing chains, we managed to reconstruct in 3D the cliff face from Pleiad images acquired at 40 degrees. We reach a cliff face point density of 1.7 points per square meter with an average precision error of 4 centimeters. This value allows the detection of faults using multi-source comparison greater than 100 cubic meter, making it possible to observe 69% of the fault around the studied area. So how to generalize the use of very high and oblique spatial imagery in order to improve the monitoring and understanding of cliff erosion is my current problematic in research. The aim is to make the best use of Pleiad imagery in terms of retreat rate, erosion modalities by developing relevant, transposable and intelligible methods for monitoring and understanding erosion. So to do that, my research is based on 2 projects, Heracles and Cicero, studying 4 sites, 2 limestone rocky cliffs in Normandy and in Zakynthos Island in Greece, and a soft cliff site in Brittany. I won't develop on this project any further today because this project will be explained in my talk of the 8th of March at the Mediterranean Women in Geomorphology virtual event. And thanks to my teaching side as a lecturer, I would like to present my work on the triptych learning, citizen science and research. Breton stakeholders are motivated to monitor indicators according to OSIRISK protocols that I previously mentioned, but lack of time to do so. Conversely, some citizens want to participate in the acquisition of scientific measurements while learning. So I proposed in 2019 to create a citizen science smartphone app to collect hazard data and provide information about coastal dynamics with the help of ISBLUE, the interdisciplinary spread school for the blue planet. With the ISBLUE help, it's able to work together students from various backgrounds on common projects.
2 minutes.
So I developed, with the help of Riwellen Ruo, educational engineer, the development of the app called Costapli for 3 years, with the involvement of 25 students to create the app, and with the help of stakeholders and citizens to test the app and suggest improvements. We are currently at the 2nd year of our project. A first version of the app is available. In-situ test will begin in spring, and we hope that at the end of 2022, the app will be ready to be used in 10 of local authorities in Finistère, in Brittany. So to conclude, my research on coastal hazard is exciting thanks to multidisciplinary and international team who teaches me a lot. The link with training and applied research is important to me, and interesting projects are currently in progress or emerging. So thank you, and to finish, I would like to see you the process of cliff failure in action.
Good afternoon, everyone. My name is Ankit, and I'm going to talk about the research title Effect of Impact Inheritance on Subsequent Rock Breakdown. I have put a video on the right side of the slide from an experiment showing how a projectile impact excavates the surface. Before starting my talk, I want to give a brief outline of my presentation. Firstly, I will introduce you all to my research question, followed by background knowledge on the subject. Then I will talk about methodology that include sample preparation and analysis techniques. And following this, I will describe a rock breakdown experiment that I conducted. Moving on, I will present results and then talk about conclusion and contribution. I want to describe a novel research question that myself and Mary come up with, that is how impact inheritance affects the subsequent rock breakdown. In this case, we focus on sandstone in semi-arid conditions. So what happens during an impact event is an incoming hypervelocity projectile collides with planetary surface and forms a crater. This causes change in physical and chemical properties of the rocks due to high temperature and pressure during the event. And when these rocks are exposed to subaerial weathering conditions, they will break down differently. During an impact cratering is one of the most dominant geological processes in the history of the solar system. During early history of the solar system, the rate of impact was very high. That is why we see so many craters on relatively less active planetary bodies such as Moon and Mars. Compared to the Moon and Mars, Earth is more geologically active. This is the reason why traces of impact events have been erased by tectonic and erosional processes. To date, there are 190 recognized impact craters on Earth. Compared to this, there are over 100,000 craters have been catalogued on Mars. Here's a figure showing the location of all the recognized impact craters on Earth. During an impact event, hemispherical shock waves are generated that travels readily in all directions through target rocks. The amplitude of these shock waves decays exponentially as we move further from point of impact due to the consumption of energy in causing deformation in these target rocks. The rocks closer to the point of impact event experience more intense shock deformation and melting. This figure on the right side of the slide exactly shows this. As we move further from the point of impact, the shock pressure contour decreases. As shock wave passes through sandstone, it results in a range of shock features that are key in identifying impact events. Here is a figure showing the classification that is used to identify impact metamorphism in sandstone at a range of pressure and temperature. Our research only focused on low shocked sandstone belonging to class 1A and class 1B, so I will only describe these classes here. Class 1 shocked sandstone experiences shock pressure of up to 5 gigapascals and temperatures of up to 350 degrees Celsius. In class 1A, irregular fractures and loss of porosity is observed. In class 1B, we find irregular fractures, and we also find that pores are completely collapsed. Meteor crater is the site where our study was based at. Meteor crater is a bowl-shaped simple impact crater located in Arizona. This 50,000-year-old crater was formed by the hypervelocity impact of an iron and nickel meteorite named Canyon Diablo. The diameter of the crater is 1.2 kilometers and it is about 180 meters deep. Over 95% of the target rocks comprises of Moenkopi Formation, Kaibab, and Coconino Formation. You can see these beautiful crater walls in the video. The top one is the Moenkopi and Coconino is in the bottom. Here is a view of meteor crater looking northwest. Moenkopi Formation is on top of the stratigraphy. Kaibab Formation underlies below Moenkopi, and below Kaibab is Coconino sandstone. These impacted rocks in the crater walls are also exposed outside of the crater that did not undergo impact. Meteor crater provides unique opportunity to compare the difference in breakdown of rocks, breakdown of impacted and non-impacted rocks in similar environmental conditions. This map here shows the location of meteor crater and control sites where non-impacted rocks are located. We focus our study on Moenkopi and Coconino sandstones. On the right side of the slide, you see the map showing the location of the samples from meteor crater. Non-impacted Moenkopi sandstone were collected from two control sites shown in previous slide, and non-impacted Coconino sandstone samples were collected from Clear Creek Reservoir 50 kilometers away from meteor crater, as they were not exposed in immediate vicinity of the crater. In this slide, I want to describe sample preparation and characterization methods used in our study. We prepared 30 micron polythene section for characterization of the samples. We also prepared powdered samples for the X-ray diffraction analysis, and we prepared 5 centimeter cube blocks for rock breakdown experiment. Sample characterization techniques used in this study were petrographic microscopy analysis, scanning electron microscopy analysis, powdered X-ray diffraction, and X-ray computed tomography. We conducted a physical weathering and desalination experiment in order to understand the effects of impact inheritance on breakdown of sandstone at Oxford Rock Breakdown Laboratory in Oxford University. The length of experiment was for 13 days. Temperature and humidity were cycled for 39 accelerated cycle, each of 8 hours duration with a step size of 1 hour. We cycled temperature from -2 to 35 degrees Celsius and relative humidity 13 to 45 degrees Celsius. On the right hand side of the slide, it's the figures D and E shows the conditions of temperature and humidity, relative humidity in the environmental cabinet. We also put a 40-watt halogen bulb 20 centimeter above the sample blocks in order to provide direct heating of rock surface by radiation. There were 27 samples, 10 samples of low sock Coconino sandstone and 13 samples of low sock Moenkopi sandstone. 2 unsocked samples from both Coconino and Moenkopi were selected. We created a sand and salt mixture bed in 1:10 ratio which was 1 centimeter thick, and we used gypsum salt, which was also found at the meteor crater site. We put our samples on top of this sand and salt bed. We also simulated rain by spraying 25 milliliter of water every 6 cycles, followed by physical weathering experiment. We conducted a desalination experiment in order to remove the salt taken during the weathering experiment. So we immersed the samples in water for 48 hours and then oven dried for 24 hours at 50 degrees Celsius. This was repeated for 3 cycles. To find out the changes due to our experiment, we used the following methodologies. We did a hardness test and weight measurements before and after the weathering experiment and desalination experiment. We took repetitive photographs during the weathering experiment and desalination experiment of the samples. We also did X-ray CT and image analysis of blocks before and after the rock weathering experiment. In terms of petrographic properties of non-impacted Coconino sandstone, it consists of 94 to 99% quartz and minor clay minerals and heavy minerals. The grain size ranges from 0.09 to 0.12 millimeter. The porosity can range up to 20%. And when these rocks undergo impact, so class 1A rocks, we see the porosity is reduced by 38% and less than 5% of the grains show wavy extinctions under cross-polar and optical microscopy. Some of the grains also show irregular fracturing, microfracturing in the grains. And when we go to the next class, which is class 1B, the 98% of the grains contain irregular fractures and porosity is 10.5%, which is reduced by almost half. The aperture and width of microfractures in quartz grain range from 0.1 to 5 micron. On the right side of the slide, you can see control samples with control Coconino sandstone sample, which is non-impacted, and then class 1A and class 1B Coconino sandstone. The blue substrate you see in the optical microscopy are the pores, and then you see quartz grains in colors and white colors under cross polars. And then next, the B, you see the class 1A Coconino sandstone where porosity is almost reduced, and then class 1B pores are collapsed, and we see more prominent irregular grain fracturing. So below these images, there are subsequent SEM images where black represents pores, and when you go from D to E, we see the blacks are reduced. That means pores are reduced. And then when we go to class 1B rocks, we see most of the grains appear to be fractured. So below is the zoom in view to show the fracturing in class 1B Coconino sandstone, and this image G shows the irregular fracturing in class 1A Coconino sandstone. So we see the difference in terms of fracturing that happens when Coconino sandstone move from class 1A to class 1B. Moenkopi sandstone consists of 50 to 80% quartz, microcline, muscovite, hematite, and carbonate and kaolinite in minor amounts. The grain size ranges between 0.009 to 0.12 millimeter. The original porosity is 5 to 8.5%. In class 1A Moenkopi sandstone, sandstone, we no change in mineralogy due to impact, and porosity is reduced by 88% compared to non-impacted rocks. Compared to Coconino sandstone, we see no irregular grain fracturing in Moenkopi sandstone. On the right side of the slide, you can see SEM image of Moenkopi sandstone. So A and B represent control samples, and C and D represent the class 1A Moenkopi sandstone. So the A is the original SEM image, and B is the thresholded SEM image, which shows the black colors represent the porosity in the Moenkopi sandstone. Similarly, if we see the amount of black spots have been reduced in the image D, which represent class 1A Moenkopi sandstone. Our weathering and desalination experiments showed some interesting results. Some of the low Coconino sandstone showed an accelerated change in rock strength and higher weight loss compared to unsocked Coconino sandstone. In contrast to Coconino sandstone, some of the low socked Moenkopi sandstone samples gain weight. However, low socked Moenkopi sandstone does not show accelerated change in rock strength. We sample rock hardness halfway through our experiment, and we find a significant difference in response of the low socked Moenkopi sandstone, which showed a decrease in strength. And however, at the end of cycle, the low socked Moenkopi sandstone showed a trend to increase in rock strength, but not back to initial values. Unsocked Moenkopi sandstone did not have this trend. So we hypothesize that this is due to higher frequency of macro fracture seen in the low socked Moenkopi sandstone that accommodates the precipitation of salts. Low socked Moenkopi sandstone containing macro fractures showed a higher decrease in strength after desalination compared to unsocked and other low socked Moenkopi sandstone. This image shows the chips and granular disintegration material from class 1A Moenkopi sandstone after the block sample was removed from the sand and salt mixture bed. We could not see the Coconino sandstone granular disintegration because the sand color is similar to the color of Coconino sandstone. Our research extends the knowledge of heterogeneities and deformations produced in rocks, especially sandstone in low sock impact environment, and it contributes to the field of rock breakdown by providing insight into the effect of low impact sock generated heterogeneities and deformation in rocks on subsequent breakdown. As impact craters are widespread on Mars, the enhanced breakdown of impactites are likely to have played an important role in landscape evolution on Mars. Our research. Thank you, everyone. If you have any questions, I can take it.
So thanks for attending to my presentation about the quaternary evolution of the Ardèche River through karst-river relationship and multi-method dating. I will present you here my PhD work that I did on the EDITEM laboratory, like Florence this morning. So I worked on the Ardèche River catchment, which is a part of the wider catchment, which is the Rhône River in south of France. This Ardèche River is also very famous because inside you can find a lot of archaeological sites, such as the Chauvet caves, which artwork was dated back to 36,000 years ago and dated with radiocarbon, which means it's one of the most ancient and better conserved artwork and parietal art in the world today. And so this cave, the Chauvet Cave, is also located in a very curious, interesting environment with prominent landscape features. We are inside an entrenched meander, the Combe d'Arc meander, which was cut off in the shape of a natural arch. So we wondered, because there is a lot of Paleolithic sites around this place, if there could be a link between the choice of occupation of this space and the landscape features. But in order to answer this question, we had to understand its landscape evolution. And because it was an abandoned meander, we started to study the geomorphological evolution of the river. So we did some field work, tracking some outcrops, and we discovered some pebbles that were located at different levels above the bedrock. So 8 meters, 15 meters, 30 meters, and 45 meters of relative height above the bedrock. And those deposits, we tried to map them at the entrance of the Ardèche River Canyon, in the Vallon-Pont d'Arc plain. So you see it, and it is right before the entrance of the canyon. Those deposits that we mapped allowed us to try to reconstruct the landscape evolution, the fluvial evolution of the river, which seemed to draw meanders that were progressively abandoned across time. Some paleo meander remains indeed show different stages of erosion. However, when we go inside the canyon, we have less and less fluvial deposits. So it is more difficult to study the river evolution. Fortunately, it is located in limestone plateau. So we did some cave investigations because some of them contain paleo-environmental archives, such as speleothems or fluvial deposits. And we tried to combine both those observations inside the same system. So we tried to build a large-scale 3D model that could involve both these kind of observations. We did some multi-method acquisitions of topography. For example, laser grammetry. Here, this is the natural arch, which was acquired by laser scanning. We performed with this method the topographical acquisition of the abandoned meander. And then, after removing the vegetation, we did some 3D meshing in order to reconstruct and look at the topography. Then we tried to extend this methodology at a larger scale. This is the entire Ardèche River Canyon, in order to obtain a larger and more general 3D model using also photogrammetry and clipping both the models to each other. And in this 3D model, then we later added the topography that were performed inside the cave systems. For example, here, this is the Châtaignier cave that is inside the Combe d'Arc abandoned meander, and which comparison with the outside morphologies can provide information about paleo-environments. We also added other kind of caves, either for geomorphological purposes or for archaeological purposes. We tried to do that on the entire Ardèche River system. Then on some places we could do easy cross sections in order to compare them both inside cave systems and outside. On some specific sites which were quite important for us, for example, here still the Combe d'Arc meander, we performed some electrical resistivity tomography geophysical profiles in order to investigate the organization of the subsoil deposits inside the abandoned meander. We plotted the cross sections, the results, inside the 3D model in order to compare what we saw inside and what we saw outside. So it helped us to interpret and to analyze morphologies, for example, channels and paleo channels inside the abandoned meander, slope deposits composed of clastic components also, and also the Talweg altitudes inside the meander. We also were able to define the abandoned pebble level inside the abandoned meander, which corresponds to the last perennial stage of the river before it was completely cut off in the shape of the natural arch. Then we tried to report all these observations in the same altitudinal scale as a reference for understanding the river evolution. For example, we added the erosion surfaces, such as the Pont d'Arc arch and the river limestone banks, and we compared them to the sediment deposits, fluvial deposits, that we located them outside the caves, and we could compare them to the cave systems at the same relative altitudes. For example, speleothems and flowstone deposits as clay and sand deposits. We tried them to interpret them according to the main driver of the landscape evolution, which seemed to be the river, with important aggradation phases and important erosion phases that were discovered when we did the geomorphological mapping. This model was extended to the entire middle and lower Ardèche Valley, which helped us to understand that it was the fluvial deposits were organized parallel to the current river Talweg, at least since the Pliocene erosion surface that was earlier defined in the literature. And with this model, in fact, we used this in order to do the second part of this work, which was the absolute dating. We did two kinds of absolute datings: electron spin resonance burial datings in fluvial sediments, and uranium-thorium dating on some speleothems and flowstones that we discovered inside the cave systems. For the ESR, electron spin resonance dating, we mainly dated two levels, which is the layer 2 and layer 3 fluvial levels, which are located respectively at plus 15 and plus 30 meters on relative height. And we tried to do the same thing inside the cave systems at the entrance and at the end of the Ardèche Canyon. We performed both ESR measurements and uranium-thorium dating inside the cave systems. Then we tried to organize all those observations and the datings, also using former results, in relative height, trying then to compare some results with other ones. It allowed us to attribute some ages to sediments that were not directly dated, using other ones at the same altitudinal level. We then tried to organize them accordingly to the main geodynamic driver, which is also the river. And then it helped us to understand that some of the main sedimentation phases seem to occur during glacial stages, and the main erosion phases also seem to occur during the speleothem growth, which means the interglacial stages. This relative chronological model and the absolute datings, we tried to combine them in a single Bayesian statistical hierarchical model in order to refine the chronology of the river deposition. And it highlighted that a lot of the fluvial aggradation phases seem to be correlated with the 100,000 years glacial, interglacial cycles, which occurred at the end of a Pleistocene period. Most of the deposits seem to, the maximum of the deposits seem to occur during the transition from glacial stages to interglacial stages. But there is also a case, for example, the second layer, which seems to occur during the transition from interglacial to glacial stage. Those models are, in fact, relatively common in the literature. It was observed in the Mediterranean area, but also in northern catchments, like, for example, in France, in the very accurately dated Somme River. So, in fact, it was a quite classic pattern for Southern River. So, this model helped us to understand the landscape evolution of the entrance of the Ardèche River. For example, here we are at the T3 level, which is 30 meters above the current Talweg. At this stage, when we do a reconstruction, a 3D reconstruction, we don't see the Pont d'Arc arch in the landscape, which means it was not existent in the archaeological landscape. It was dated to marine isotopic stage 6. Later, we discovered an erosion phase, which is still present and that we can see with the geophysical survey. And the erosion mark means that it still went inside the meander at this interglacial period. Then later, there was another sedimentation period, which dates back to 130,000 years, maybe MIS 5D or E, and which corresponds to the last stage of the meander perennial activity. After this age, the Pont d'Arc arch is open in the landscape, and the meander is definitely abandoned, which leads to slope dynamics that were observed both in the geophysical prospection, and in the 3D model. Finally, the meander is sometimes reflooded during very important floods in the Holocene. All of the floods were dated to the Holocene until that's what we know until now. And the last time it happened was in historical period in 1890.
2 minutes.
So those results allowed us to understand that the Chauvet Cave inhabitants saw the arch, which means this particular feature that we know today was partly visible for them during their occupation, dating back to 36,000 years ago. It means that maybe landscape was also important for the past societies. We don't exactly know the meaning, but we can now work in order to discover these kind of things, thanks to geomorphology. So this is also a representation of maybe what could be the Pont d'Arc system and the Combe d'Arc system during the cutoff, the meander separation that we can achieve through 3D modeling. And to sum up the results, we try to highlight the interest in this presentation of mixing karst-river data and observations, because they can combine each other very well, especially when there are some lack of information in one system or another. The interest also of 3D geomorphology in order to integrate all this data all together. And finally, maybe I discovered it later in my PhD, the great interest of performing Bayesian statistical modeling, because having such numerous data helped us to build relatively strong relative chronological model that helped us a lot in refining the absolute chronology. And I thank you very much for your attention.
Perfect. All right. Yeah. Hi, everyone, and welcome to my presentation. We're taking a small detour to Mars before we go back to Earth, like Mauro said. But I'm basically going to be focusing on early Mars paleo lakes, so ancient lakes on Mars. And I'm specifically going to be talking about how the morphology of these lakes can be used as a quantitative record for characterizing early Mars climate. And so, as some of you might already know, there is significant evidence for fluvial and lacustrine activity and features on the surface of Mars. And this suggests that there was abundant liquid water flowing and accumulating a really long time ago, up to billions of years ago on Mars. And so, for example, in this image, which is somewhere in the mid-latitudes on Mars, you can see that some of these fluvial geomorphic features are quite clear. And usually we can separate these into two types. For example, we have valley networks on Mars, which are these deep valleys that were carved by ancient rivers. But you can also find sedimentary landforms such as deltas or fans, which show that the sediment was deposited in a standing body of water. And so, you know, you get both sides of the coin here. However, previous studies that do look at the morphologies of these geomorphic landforms, for example, if they're looking at valley networks, they use this to calculate the total amount of water that's cycled through the valleys globally. And then others will look at these channel morphologies and say that, this was the peak runoff rate that was required for these channel morphologies or the formative discharge. So generally what you get is that, you either have a cumulative amount of water or this sort of instantaneous amount of water that was required. So generally, as you can see, there's these two sides of the spectrum. So there's not really intermediate constraints on how much water was actually available on the surface of Mars at a time, and also for how long. And so instead, one way to try and constrain this sort of intermediate water amount is by looking at paleolakes. And so paleolakes are impact craters on Mars that form these basins, and water naturally fills these basins. And so in particular, we're going to be looking at these paleolakes that are actually fed by valley networks themselves, which suggests that the water that was filled into these lakes was sourced from precipitation, which could be either rainfall or snowmelt. And so we'll be focusing on those. And so really the question that this work seeks to answer is, what was the intensity and duration of a favorable climate event on Mars? And really this is kind of two different questions. And the first question, which is the case of intensity, is something we sought out to answer in our most recent paper that was published last summer, which is basically, how much precipitation can actually be supported by these lakes. But the focus for this talk is going to be on the second part of this question, namely looking at the timescales that are required to form the lakes that we observe. And so the way we do this is by combining these geological constraints, these the lake mapping features that we use, also combining this with climate model data to try and derive quantitative estimates for timescales for all these systems which are distributed across the Martian surface. And so this is also kind of the broad format of the talk that I'm going to go through with you guys. And so presently on Mars, there's actually hundreds of paleolakes that are mapped. However, only a small subset of these are fed by these valley networks that you can see here. So just about 100 of them are actually suggestive of surface runoff or liquid water on the surface of Mars. And so like I told you, these lakes form in these natural depressions formed by impact craters, but they can also be divided into two types. You have your open basin lakes and your closed basin lakes, and there's about half of each in our database. And so an open basin lake, basically you have the inlets flowing into this basin, but what you also have is an outlet canyon. And so what this means is that the lake filled up to the top, overflowed and breached, and this caused a catastrophic erosion of a rim out of the lake basin. However, in closed basin lakes, there's actually no evidence of erosion on the rim. The rim of the crater stays essentially uneroded. So we call this a closed basin lake. And so what we can do is to measure morphological parameters of these lakes. So things like this lake area, the area of the watershed that feeds water, where we can see these valleys are eroded into it. And we can also measure the basin of this crater that you can see here. And so importantly, these two types of basins also provide us with two bounding hydrological limits. So if you think about it, this open basin lake, this basin volume is actually the minimum amount of water needed, because we know that the lake had to fill up to the top and then overflow to cause this overspill and this canyon erosion. Whereas the volume we measure for this basin is actually a maximum volume, right? Because we know that the water never filled to the top and never overflowed. So maximum and minimum volumes, that's sort of the main limits that we're working with here. However, there's also a third type of lake basin that we have identified on Mars, and we classified this as a coupled lake system. And essentially what this is just an open basin lake which breaches and then flows into a closed basin lake that is downstream. And an example of that is this one here. So you can see here these channels flowing into this open basin lake. There's a small breach that has been eroded and flows into this closed basin lake which never breaches. So there's no valleys flowing out of it. And so despite their sizes not being too dissimilar, one overflows and the other one doesn't. And these systems are really hydrologically important because you can basically get an estimate of maximum and minimum amount of water in the same location at the same time. And so I'll just go through this briefly. This in the previous work where we try to calculate how much precipitation these these lakes could hold, essentially because, you know, we've got all these open basin lakes in blue and closed basin lakes in red, but in white we have the few coupled lake systems, and what they give us is essentially a minimum amount of precipitation that was possible. So that's this PT, or precipitation total amount in meters, which is sometimes like tens of meters up to a few hundred meters, but of course this is variable in space. And so just to kind of give you a brief description, when I say PT, it really is the sort of total local runoff amount during a runoff episode. And so what I'm really going to do next is to delve into this concept of a runoff episode. So, you know, this value of T, which is, you know, we don't really talk about how long it is in our previous work, but we want to find out ways to figure out, okay, so you have this amount of water, but for how long is that water being supplied into these lakes on Mars? And, you know, how can we define this value of T? And so, so on Mars, when we talk about runoff and, you know, basically this episode duration T, I just want to remind you that we're not talking about peak runoff again, or the cumulative total runoff over the entirety of the lake lifetime, but it's simply the amount fed during into lakes during a sort of single quasi-continuous episode. And so I'll show an example of this. Another way to think about this is looking at it graphically. So on Mars, we think that climate was probably sort of quasi-cyclical, where there was episodes of more runoff and less runoff. So, you know, something like this, some oscillating climate, which produces runoff over time. However, if the events are never long enough or intense enough, they will never cause an open basin lake to breach. However, if there is a single event that is long or intense enough, then this will actually cause the open basin lake to breach. And it's this threshold event that characterizes this total minimum precipitation depth that we calculate for this runoff episode. And this is defined as our runoff episode T. And note this, you know, these values don't provide any information on other events. It's just on this threshold event. And for closed basin lakes, the idea is similar. You have this oscillating climate, but there is never an event that is long or intense enough to breach the lake. And so this gives us information about the maximum amount of precipitation that could have occurred for this lake, again, over the same time period of T. And so again, for a coupled system, which contains both an open basin lake and a closed basin lake, we know that T, the time they were active for, and PT, the precipitation supplied to both of them, is the same because they're hydrologically connected, and so they're spatially and temporally coincident. And so this allows us to investigate their hydrology and the timescales in more depth. And so I'll show you an example of this. One way to look at this is to examine how lake volumes of both lakes in a coupled system vary over time. So this VL, or lake volume, as a function of T. And so here in the x-axis, we won't look at absolute timescales, but we'll look at this sort of dimensionless time, which is just time after breaching, where this breaching time is here at this one value. And in the y-axis, we just have the lake volumes. So what do these lake volumes look over time relative to the breaching? I'll take you through this. Essentially, we have the open basin lake. Before any breaching occurs, the open basin lake is simply gathering water and filling up proportional to its watershed, which is this watershed you can see here. However, once the lake volume reaches the size of the basin, which the basin can hold, of course, it overflows and erodes and breaches, and some amount of the lake volume is transferred downstream into the closed basin lake. So it erodes a little bit down here and transfers that lake volume down to this basin. So this volume is the same as this one. After that, the open basin lake basically stays at the same level because any input will basically flow out again. But now the closed basin lake has actually captured this watershed too. So after this breach, the closed basin lake will be increasing at a much higher rate, which is basically the combined watersheds. However, it can't keep increasing forever because, again, we have this total volume of this lake basin, which it can't reach because we know the closed basin lake never overflowed. So although it keeps increasing, there's essentially a range of timescales for which it can keep on accumulating runoff because we know it never eroded. So we end up with this sort of defined range of permitted timescales, which tells us that runoff had to be a sort of discrete event. And for example, for this system, we find that the permitted runoff episode, or the time after breaching, could only be about 44% than it actually took to first breach this the first lake, which is quite short. And so these relationships give us an idea of the relative lake timescales, at least with regards to filling and breaching and subsequent overflow of the lakes. But how can we go about actually quantifying the duration of this runoff episode T on Mars? And so here I show a simple way that we can tackle this. First of all, we have the precipitation amounts for our lake basins, which are determined by their sizes. And second, another constraint we have is actual precipitation rates from global climate models on Mars. So this one, for example, is from Robin Wordsworth in his 2015 paper, and it's basically just spatial distribution of rainfall across all of Mars. And so quite simply, if we've got a precipitation total for an episode and we've got the precipitation rate, we can basically just use that to solve for the total episode timescale using this relationship. So for example, an episode in amount of years. And so suppose we have this global distribution of precipitation. What we then do is to find the precipitation rates in each of our basins to find what the actual runoff rate at that location was for each of our coupled lake systems. So each basin has its own local or regional precipitation from these models. But also remember that there's a range of permitted timescales for each coupled system, so it's not just one defined value. And we also have about 7 coupled systems. So essentially, depending on lake morphologies, we'll have different range of permitted timescales for all of our 7 coupled systems, which is kind of shown schematically here. But essentially what we want to do is to kind of build a histogram of what timescales most coincide with the most lakes and which ones coincide with the least lakes. And so a histogram like that would look something like this. And I'll take you through it again. For example, here in the x-axis, this is the duration of the episode in years. And in the y-axis, that tells us how many of our 7 coupled systems we found are satisfied by that time bin. So for example, here, a episode duration of only 10 years only satisfies 1 lake system, which isn't very good. However, an episode timescale of 100 to 200 years actually satisfies 5 out of our 7 coupled lake systems. And so that would make this sort of time bin the most permissible or the most probable time bin that we have for this model, at least. But we can not only do this for a single scenario, we also have other climate scenarios on Mars. So for example, Wordsworth actually did different models for rain and for snow, and we get different episode durations for these and different distributions. Not only that, but we also have completely different models altogether. So Kamat et al. Looked at how atmospheric pressure changes runoff, and that again results in changes in our episode timescales. We also have, for example, how the initial water inventory in global climate models affects the runoff. You can see here the difference isn't too much, whether it's 10 meters or half a kilometer of water covering Mars. And also, if we think that the climate was generated from a giant impact crater, that can also generate heat and runoff. And so these are the results if we use different sized impacts on Mars. And I don't have time to, talk about all of these models, so I'll just show you what they kind of look like superimposed on each other. And I just wanted to point out some key observations. The first is that you'll notice that the most permissible timescales seem to most commonly lie between 100 to about just under 10,000 years for a single runoff episode on Mars. And I remind you that you actually need many of these episodes on Mars to be able to carve the deep valley networks that flow into coupled systems. So this couldn't have just been one episode. It had to be a long geological timescale of integrated several episodes integrating into the topography. So you'll need basically this amount of time multiplied by a certain order of magnitude. And second, there is not a single timescale that actually satisfies more than 5 coupled systems out of the total of 7, which is still an interesting result because it could mean that either there wasn't a single timescale that's valid for all our coupled lake systems, so they could have occurred in different episodes or episodes of different durations, or it could also mean that there's more space to explore other models that could satisfy more of these systems. And this is something that we're looking to try next as well. But so basically, I just wanted to take you through some of the key points of this research.
Your conclusion, please.
yeah, sorry, conclusion. Calculated all of these precipitations for these systems. We use their morphologies to show that runoff has to be bounded in time. We can combine this with models to generate actual timescales, and finally that this has important implications for actually testing climate models on Mars because we've got these localized markers. And yep, that's it from me.
Good afternoon to everyone. Today I'm presenting the results and the follow-up of my PhD research. And my question was why integrating land and sea spatial data set is so important. First of all, to reach a holistic view for the processes occurring on the coastal, nearshore, and shallow water areas that are interconnected to each other and are affected by processing originated both on land, such as fluvial processes, and marine environments, waves, tides, leading to a geomorphic change and to geohazards, mainly related also to the ongoing climate change and economic development. But the main challenge is providing a seamless elevation data, digital elevation models, digital terrain models that could couple multi-source data sets with comparable precision and accuracy. And this is also difficult for different accessibility and the investigation costs among the terrestrial and the marine environments. Indeed, on land, we can have geomorphological maps that are largely produced for many areas and are crucial for georisk assessment and land management and other geomorphological field. While at sea, we have less than 18% of the world seafloor that is surveyed at 30 arcsecond resolution, and less than 9% of world seafloor that is surveyed with high resolution multibeams, that is a resolution comparable to the one reachable on land. So the integration of terrestrial marine spatial data sets can have different applications. Going from geohazards to geoarchaeology, coastal planning, late-quaternary changes of coastal landscapes, geomorphological mapping, marine and landscape ecology, and geoheritage and diversity. This is an order of frequency of work papers that could be found on literature on this topic. In this presentation, I'm going to show you some case studies, some applications of this integration, starting from the geomorphological mapping. Okay. So during my PhD, I analyzed the geomorphology of terrestrial and marine areas of the Maltese archipelago, focusing on two areas, the northern Malta and Comino. Malta is the main island of the Maltese archipelago in the central Mediterranean Sea, and the northeastern coast of Gozo, the second island of the Maltese archipelago. Here, the main challenge was building a legend, a geomorphological legend that could highlight the emerge and submerge features. So here we adopted the guidelines of the Italian geological surveys for the terrestrial geomorphology, for the terrestrial part of the geomorphology. And we decided to apply the same symbology, but with lighter colors for the submerged features, in order to give also a visualization of emerged and submerged areas of the study areas. Then we focused on the geomorphological evolution of the Maltese archipelago since the last glacial maximum, and using the sea level sea level changes recorded in a site close to Sicily Island, and published by Lambeck et al. 2011, we were able to reconstruct the sea level oscillation during different time frames. In particular, during the last glacial maximum, the Maltese Islands were interconnected to each other since the sea level was lower, about 100 meters lower than today. And the entire archipelago was linked to Sicily through a land bridge that also had the role of migratory route for quadrupeds, mammals, and so on. Indeed, we were able also to make an artistic reconstruction of a former fluvial environment, exploiting paleontological data found in Maltese caves. Then we focused on the coastal block slides affecting the northwestern coast of the island of Malta. Here, these block slides continue on the seafloor, reaching a maximum depth of about 40 meters. So the main part of this runout is now submerged. Using cosmogenic exposure dating, the chlorine 36 in particular, due to the limestone, to the carbonatic lithology of the area, we were able to date some main detachment of two sites, Anchor Bay and Harraba. In the first site, Anchor Bay, we dated the most ancient detachment occurred during the last glacial maximum, 21,000 years ago. And then two secondary detachment events occurred 9,000 and 7,000 years ago. While at Carraba, that is this peninsula, we dated two detachments occurred 15 and 10,000 years ago. So referring to the sea level changes recorded by Lambeck et al. In 2011, we were able to propose two different hypotheses for the block slide evolution. The first one refers to the classical lateral spreading block sliding model, while the second one proposes a first large-scale detachment occurred when the sea level was much lower than the present, and in much wetter climatic conditions, or maybe also an aquifer was hosted in the limestone plateau. Then, during the sea level post-glacial sea level rise, it is possible that sea level influenced the clays, the underlying clays, thus triggering secondary detachments. Then going to the geohazards, always focusing on the block slides along the northwestern coast of Malta, we were able to produce a susceptibility map of block slides. We exploited the persistent scatter interferometry results, and we weighted different factors that could influence the triggering, the evolution of these block slides, and we were able to produce the block slide susceptibility map. Then we move to the marine and landscape ecology, that is habitat mapping in marine or terrestrial environment. This is usually done exploiting, in marine environment, exploiting bathymetry, terrain attributes, acoustic seafloor backscatter, in order to infer at least the physical attributes of an habitat, of a benthic habitat. Then we could also add the biological information, and then oceanographic data, and so on. So this is a multidisciplinary research that is usually carried out for marine conservation with different directives at European and international level. So for the Maltese Islands, we analyzed the seafloor acoustic backscatter of the seafloor, and we automatically classified this data, validated them through grab samples collected from the seafloor, and we were able to produce a sedimentary coverage of the seafloor of the Maltese Islands that was a support for the geomorphological maps that I showed you at the beginning. So integrating terrestrial marine spatial data sets is really useful, but has the main challenge of providing an homogeneous continuous representation of land and seafloor, especially covering the intertidal zone, that is the so-called white ribbon, since it is really shallow, too shallow to be served with a traditional acoustic method, but is too deep for other terrestrial methodologies. So we, fortunately, in recent years, there are new advances in acoustic systems that could allow high resolution surveys in shallow water. Specifically, there are multi-transducer multibeams, interferometric echo sounders, multi-phase echo sounders. Then also technological improvement, such as the visualization for images and data collected with the optical sensors, such as the bathymetric LiDAR and the underwater photogrammetry, could allow to obtain elevation data of shallow water areas with really high resolution. Finally, thanks to different research funding programs, sharing data is really appreciated and encouraged in recent years. So we can also exploit already collected data and also update them maybe. Concluding, terrestrial landscape and landforms are always being investigated and benefited from high accessibility surveys of the area and high resolution data, while submarine environment always struggle to be represented, at least with the same resolution and coverage as their terrestrial counterpart. However, new technologies and techniques are now contributing in obtaining a seamless digital elevation models and digital terrain models for land and sea areas. And standardization and harmonization of data are the next step for to adopt a common terminology and a classification scheme for both terrestrial and marine areas in order to be more as much comparable as possible. Finally, the awareness on the interconnection between land and sea environments is now increasing and leading to a holistic approach for understanding this changing environment and also for a better environmental protection. So thank you very much for your attention.
Great, thank you very much. Hopefully you can hear me okay.
Yes, it's fine.
So thank you very much for the opportunity to discuss some recent research on seismic geomorphology offshore Greenland. This is not my work alone, it's a combination of my work with colleagues, so I'd just like to tip my hat to them to say thank you for their efforts. So I'm mainly going to be focusing in this area up in offshore Northwest Greenland in the red box. So a little background is always helpful, so, and I'm sure I'm preaching to the choir here, but we study ice sheets because they are potentially unstable, particularly their marine parts. And of course, everybody knows that they can impact global sea level and climate. And that's really important because at the moment, we already know that the Greenland ice sheet is experiencing more days of melt, and that's shown on the left-hand image here. And in Antarctica, we're also seeing evidence of potential changes happening in the West Antarctic ice sheet as well. There's a problem in that we only have a limited amount of information on whether these changes are common or unusual because the observational records that we have are too short. Now, fortunately, the geological record can provide us with some hints on this. So most high latitude margins have two common large-scale features. The first is cross-shelf troughs, and these are major erosional features formed by the advance of ice streams offshore. And you can see on the right-hand image here how the continental shelf around Greenland is incised by these large troughs. So if you can hopefully see my mouse here, you've got them crossing the shelves here. And at their distal end, we have what are called trough mouth fans. And these are major accumulations of material that takes the form, such as in the schematic on the left. So you can kind of see these bulbous shapes at the end of some of the troughs in Baffin Bay. And these contain many of the eroded materials from the excavation of the trough, but they also contain materials that have been transported by ice streams from elsewhere on Greenland. Now, they typically contain a record of multiple glaciations, so they can go back to maybe even 3 million years. Now, the method I use is seismic reflection, and I always think it's helpful because some people panic with seismic as to exactly what it is, but I'm sure everybody here knows. But basically, it starts with the generation of a sound wave. Some of that energy goes down and bounces off of the seafloor. It returns to the surface where it is then recorded. Some of the energy actually goes further down beneath the seafloor, and it reflects off of the next geological boundary and then returns to the surface where it's recorded. And that method allows us to capture information on what the geological structure is beneath the seafloor. And essentially, these different seismic reflections, so you can see it on the image there, all these different layers, we can think about them as paleo seafloors. So the research presented here is from the Melville Bay trough mouth fan offshore northwest Greenland. And on the left here, the map shows the Melville Bay trough. So that's this incisional feature going from the right to left. And then you can also see this large bulge on the left-hand side where that's our trough mouth fan. Either side of the cross-shelf trough, you've got these raised areas. So you've got the northern bank here, the southern bank, and then there's another trough slightly to the south called the Upernavik, and that's the evolution of that trough is also closely associated with the Melville Bay trough. On the image, you've got these dashed lines. These are the outlines of the 3D seismic data that are used in the study. And then the white lines are 2D data. So on the right-hand side, in the top right, we have a seismic profile going from the southwest on the left to the northeast on the right. And that's labeled 2A on the map. So you can just see it with this black line here. And that captures some of the trough and also a tiny part of the bank to the north. Then beneath that, there is a profile with the same orientation, and it's labeled 2B. So that's the second black line here. And that captures the southern part of the trough. So the glacial stratigraphy here, when we look at these seismic profiles, so the stratigraphy that comprises the trough mouth fan can be separated into 11 separate units, and these vary spatially. So in the north, so if you look at the upper seismic profile, you can see that there's significant topset erosion. So there's a major unconformity at the seafloor here. And then if you compare that to slightly further south, and it's easier to spot on the interpreted profile, you can see that lots of the top sets are preserved. So there's a variation in the preservation of the different units. So in different places, we have different parts of the strata. Panel A on the left here basically shows the main depot centers that are associated with these 11 separate units. And you can see that during the initial deposition of the fan, so that's it starts at A1 through to 11, and A1 through to A4, they're separated. So we have some depot centers on the Melville Bay Trough, but there's also some in the Upper Narvik Trough to the south. And then by the time we get the deposition of units A5 to A7, which is in the middle here, we can see that they merge together and they're a big elongate deposit. And then after that, they split apart again. So the two troughs, their evolution are very closely linked together. On panel B on the right-hand side is a thickness map for the entirety of the trough mouth fan. And in places, the glacial sediments here reach up to 1.8 kilometers thick. So there's a huge archive here of potential glacial and interglacial cycles and transitions that we tried to harvest to find some information. Unfortunately, in this area, because it's quite high latitude and it's fairly isolated, there are only very limited dates for the stratigraphy of the fan, but we are reasonably confident, and I use the term reasonably very loosely, we're reasonably confident that formation began at about 2.7 million years ago. And then we also have a date for the top of unit A3, so that's just here, at 1.8 million years, and that's related to a magnetic reversal. All the other boundaries for the different units, which are shown by the red lines, are estimated from linear sedimentation rates. And using this 3D seismic data, it's possible to image buried landforms, and we can interpret them in a way that we would actually interpret modern bathymetric data. So here are some examples of grounding zone wedges, and you can see the interpreted and uninterpreted seismic profiles. So these landforms are atop some unconformities. So hopefully if you can see my mouse again, you can see the top of A3. Some of these reflections are truncated. And then on top we have this, the blue dash is the outline of the landform, and we can map them in 3D. These features measure up to about 90 meters thick, and we can image some of their internal geometries so we can get an idea of how they're formed as well. And the documentation of grounding zone wedges is quite useful. It's important because it tells us the location of the ice margin at a particular time. And it also tells us that the ice margin was actually stable for a period of time. On a number of the reflections or the paleo shelves, there's also evidence for megascale glacial lineations. And these are landforms that are directly associated with fast flowing ice streams, and they provide us with information on ice sheet velocity and also the directions of ice sheet flow. Now they're displayed here at the bottom as these linear features on shaded relief maps. And this data is so high quality they could actually pass for just a bathymetric image, but they are in fact actually buried about 200 meters below the seafloor. So the average orientation of all these different megascale glacial lineations and the depot centers, which are shown above them, they gradually move northwards through time. And that's showing us that the pathway of the ice stream gradually migrated. Now there's several sets of lineations, not just those ones that are shown here, but they're shown on the graph on the right-hand side with some general estimates on the possible ages. That's the different colored circles there, along with some error ranges. You can see the errors are quite large, hoping to one day be able to tie that down a bit more. But the rose chart at the top shows the average direction of these different lineations, and we can see that it changes through time. So we're able to see where ice is flowing and how that changes through time. And we see also in the other data, so the migration of these ice streams is reflected in this spatial variability of erosion. So you've got the profile on the left and it's shown by the red line on the right. So the changes in the lineations suggest that the main trunk of the ice stream gradually moved north, and we see that in the seismic data as well. So on the northern part, we see again this truncation, but on the left, or in the south, we see evidence of topset preservation. When we move a bit further towards the basin on the paleo slopes, there is an abundance of evidence for gullying. These images show a number of incisional features on the slope, and they're thought to, or at least according to me, I think they relate to hyperpycnal flows from dense sediment-laden glacial meltwater. They're imaged here using a number of different geophysical techniques on planform maps, but you can see on the seismic profile in panel E how they've cut down into the stratigraphy, so that's the little blue line. There's also evidence of some slope instability with the debris lobes shown on panels C and D, so that's these little black areas, and we think this relates to slope instability that is associated with lots of materials being rapidly delivered to the shelf edge by these ice streams. The gullies are remarkably common in the stratigraphy, so the seismic image here shows all the main units marked in red, and within each of those units we have lots of reflections which are marked in blue that have these gully features on them. So this tells us that hyperpycnal flows related to glacial meltwater were very common throughout many stages of the Pleistocene. And a finding such as that is fairly interesting because it's quite a high latitude location. So we might have originally expected that discharge from the ice sheet might have taken place as icebergs rather than melting, but seemingly there was a lot of meltwater around. And then moving as far basinward as we can, we've got deposits at the bottom of the slope that display some wavy geometries, and they appear to be linked to a combination of downslope and possibly along slope processes. They're perhaps related to the gullies further up the slope and maybe the formation of turbidity currents perhaps. So there's work still to be done on these features in particular because we've only recently just got data associated with them. And then the final landform is there's a very small number of examples of iceberg scours buried in the stratigraphy, and they're formed when an iceberg basically scratches along the seafloor because it's just large enough that even though it's buoyant in the water, it can carve into the seafloor sediments. And they're a lot less common here compared to other high latitude margins, which is quite strange, but actually it fits reasonably well with the fact that we appear to be observing all of this meltwater from the gullying. So potentially there's a very different type of discharge setting here of the ice sheet than we would perhaps expect. I don't want to dwell on these, this is the last slide, I don't want to dwell on the images too much as it's a bit okay, thank you. It's a little complicated, but essentially we can split the evolution of the trough mouth fan into 4 separate stages. And within each stage, the types and the frequency of landform observations give us some good ideas on what the most important processes were. So evolution between these different stages varied through the interplay of glacial erosion and deposition from one glacial cycle. And then that also had an important influence on the dynamics of the ice sheet during the next glacial cycle. So we see the characteristics of one glacial stage are not driven just by the climatology of that region, but also by the geological legacy of past glacial processes. And then just to finish up, I have to say thank you to funders, data providers, and software donators. So these sorts of data cost tens of millions of pounds to collect. So we obviously have to work with the industry for that. And also a shameless plug to a number of papers that relate to all of this work and seismic. So we've been able to image different landforms from all of these glacial ones to submarine landslides from 40 million years ago. So you can see that on the image on the left-hand side here, where we've got large chunks of what was a spit breaking off and flowing down the slope. And all of these landform records have been crucial as they've helped us to plan site locations for a recently approved IODP proposal to go and collect sediment cores from this region. So it shows that, geomorphology is remarkably useful for understanding not just how the process is going on at the Earth's surface, but also how we can dig further into the geological past. So thank you very much for your time, and be very happy to take any questions.
Hey, good afternoon to everyone. I'm just finishing my PhD at the University of Naples Federico II, and the talk of today is about raised marine terraces along the Tyrrhenian coast of southern Apennines and its tectonic significance. For who is not familiar with the geology of Italy, just let's start with a short introduction of the structure and tectonic evolution of the southern Apennines. Well, the southern Apennines are a fold and thrust belt resulting from the latest interaction between the African and European plate. And the accretion of the southern Apennines wedge took place from the early Miocene to the early Middle Pleistocene due to the deformation of the Adriatic westward subducting margin. Starting from the late Tortonian time, the shortening in the chain has been coeval with the extension that led to the opening of the Tyrrhenian back-arc basin with the formation of oceanic basins and the drowning of the innermost portion of the chain. The late Tortonian Middle Pliocene rifting in the Tyrrhenian basin was characterized by an east-west oriented stretching direction from the Sardinian margin to migrate eastwards. From the Middle Pleistocene, rifting, the shortening in the chain is not more active, and it was followed by a northeast-southwest extension and the uplift of the foredip. In uplifting areas record the geomorphological features such as raised marine terraces and tidal notches, which may provide information to reconstruct both large-scale and differential vertical motion. Of course, many studies have already been carried out along the southern Apennines coasts, and from literature is known that the Sorrento Peninsula and Bulgaria mountains are considered stable areas since at least the last interglacial period, while on the other hand, on the Ionian side, regional and local faults contribute to strong uplift, as evidenced by the flight of raised marine terraces, which stands up to some hundreds meters. To better define the long-term quaternary vertical motion and the tectonics of the Tyrrhenian side of southern Apennines, the attention was devoted to two areas poorly constrained and with a still open debate. New outcrops have been identified and characterized with this study. The morphotectonic approach has been carried out by integration of morphostratigraphical study with new U-series dating. For the geomorphological part, detailed topographic and IIM maps have been used. The first area is the northeast border of the Campania coastal graben, which formed during the early Pliocene as a response to extensional processes. The vertical motion of the horst blocks are still poorly constrained. This is due to the widespread occurrence of Holocenic pyroclastic deposits from the main volcanic complex of the Vesuvius and the Phlegrean fields, which blanket the plain and all its border. So even if the tectonic evolution of the Campania plain has been the object of many studies, however, most of the information are inferred from subsurface data, while very few surface geological information exists. The first surveys allow to recognize and map a flight of marine terraces along the Fellino Ridge. I'm going to present some of the main outcrops. And let's start from the eastern part. This is the only area with some geomorphological evidence marine reshaping. In fact, as you can see here, there is a wide flat surface interpreted as a marine terraces at around 200 meters. It is covered by a thin layer of marine sands, and which contains Ammonia parkinsoniana, Globigerina, and Elphidium crispum, so marine specimens. In all the other part of the Monteferrino Ridge, we can see the outcrops just in some new quarry. And for example, the two T2 marine terraces spans between 80 to around 100 meters, and it was found in different places along the ridge. It is formed at the base by basalt conglomerate, which evolves to marine deposits. Facies and then it's covered by continental deposits. Facial analysis allow to distinguish an alluvial fan deposits, and then in the upward parts a slope breccia deposits. So the T2 is the marine terraces. T2 is displaced by two sets of faults. One with east-west striking normal faults, and a second set with north-northwest both normal and strike slip faults. In order to date this terrace was dated with U-series methods, a calcite vein contained into the marine sands. So we know that the sands that this terrace is at least older than 260 kilo years. Finally, the lowest marine terraces, T1, well, it was founded in just in few places, and also in this case, at the bottom we can see a well-rounded pebbles, so a basalt conglomerate, which evolves to a thin layer of marine sands with some fragments of shells, and we also found some Ammonia parkinsoniana in this. So in order to give a chronological framework at such marine terraces, the synchronous correlation of multiple paleo shorelines methods has been used. It found the best fit between the elevation of mapped paleo shorelines with the supposed elevation by global sea level curves by iteration of uplift rate. So it was used in the study area. With these methods, we can correlate the upper marine terraces in the eastern part at 200 meters with the T2 terrace and provide an age of 340 kilo years, while the lowest marine terraces has been indirectly dated as 240 kilo years. We can see that the T2 marine terraces presents the elevation of the T2 marine terraces varies along the Monteferrino Ridge, well, at the strike of the Polvica fault. This variation could be seen by an uplift rate change along the strike of that fault. To summarize the first case study, a marine terraces sequence has been identified and characterized for the first time along the border of the Campania Plain coastal graben. providing constraints to the tectonic history of the graben. Based on the synchronous correlation methods, the T2 marine terraces is correlated with -9 and T1 with -7. The Polvica Falls shows a long strike slip rate variation with a mean uplift rate of 0.3–0.6 millimeters per year, and has been demonstrated that such late-quaternary marine terraces has been displaced by faults. So we can consider that Polvica Fault is still active. Now let's move to the northern Calabria in southern Italy. This is a key area because it's placed between the Campania coastal belt in the north, which, as we see before, it's considered stable, at least from the last interglacial, and the southern Calabria, which on the contrary experienced a strong uplift. But the boundary between these two areas is not well defined. In the area, even if a flight of marine terraces up to 170 meters is well known from literature, most of the marine terraces here are undated, and so both the chronological framework of relative sea level marker and the quaternary uplift of the study region are still debated. In fact, Westaway estimated an uplift of 1 millimeters per year for the last interglacial period, while other authors related the highest marine terraces to the early Pleistocene, so based on some chronological framework. In this case, also the integration of geomorphological and quaternary stratigraphy analysis on marine terraces and associated deposits allow to a reassessment of the paleo shoreline, standing a few tens of meters above sea level, in the range of 0 to 60 meters. Mineralogical and geochronological analysis has been carried out on corals and speleothems, and starting from the lowest marine terraces up to 5 meters. This terrace is visible just in the northern part of the study area, and it's formed by biocalcarenites bearing Cladoca cespitosa corals, which have been dated with the U-series methods, and evolves to a paleosoils and then some hundred meters of alluvial fan deposits. Just a few kilometers south of the first outcrops in Marina di Maratea area, we can still see the abrasion platform of T1 at 5 meters, where we can see also its inner edge. And above it, there is a biocalcarenite deposits, also contain corals, but in this case, the mineralogical analysis demonstrating that they were alterated, so we can't not date. And yeah. Also in this case, we can measure the inner edge of the T2 marine terraces. The same order of terraces we can see in the southern part of the study area. Here we have here we could date the corals. And also we can strong the analysis with a calcite with a speleothems that cover the biocalcarenite bearing this deposit. The third order is at about 20 meters above sea level. Also here we have a wave cut platform covered by biocalcarenite with corals, dated also in this case. then along the cliff of Castrocucco area, was measured the top of the Lithofaga holes and correlated with a speleothems which has been bored by Lithofaga, and was dated the speleothems in this case. And then in Torrefutes area, we dated corals at around 35 meters. Finally, the upper paleo shorelines, T5, we have speleothems that cover a marine conglomerate and Lithofaga holes, and also in this case were dated speleothems. So the U-series data point to correlation of dated corals with warm stages of late Pleistocene with while speleothems fall in the age of cold substage. In particular, the new data allow correlation of T1 with MAIS6E, the T2, T3, and T4 with with different stages of MAIS5, and a tentative correlation of T5 with MAIS7. A relative sea level curve was reconstructed and calculated an uplift rate of 0.24. And also the new dating allowed to reconstruct some eostatic sea level for this area. So I am concluding with this study. New marine terraces dating in the Tyrrhenian margin of northern Calabria Basilicata has been provided. An uplift rate of 0.24 has been evaluated. Evidence for the post last interglacial uplift bears minor implication on seismic other assessments for the study region. It's reported for the first time the occurrence of raised MAIS6E parashorelines in the Mediterranean. Relative sea level curve has been reconstructed, and the elevation of some late-quaternary peaks have been inferred. And I'm concluding the new data go to fill some gap that there was in literature, in particular for the Polvica area, and better define older datation. And we can see that during the Middle Pleistocene, the horst blocks of all the Tyrrhenian side were in uplifting, while the coastal gravens were subsiding. While during the last interglacial period, we can see that almost everywhere it's stable or quasi-stable, but some few areas present some uplifting, still they are still in uplift. So thank you for the attention.
Thank you very much, and thank you for the opportunity to talk today. I've got to start by again saying that this work is co-authored, and I have to acknowledge my co-authors at the University of Dundee, the University of Loughborough, and Nottingham Trent University for their work on this project. And I'll introduce some of the published work at the end of this presentation associated with those co-authored papers. Today I'm going to talk about some of the work we've undertaken to quantify how ice-cored landforms evolve in the high Arctic at high Arctic glacier margins. I'm going to start by giving you some research context as to why this research is important and of interest, before going on to talk about some of the methods and results. If we think about the record of glacier change that's left by moraines in terrestrial settings, by glaciers in terrestrial settings, moraines allow us to understand long-term glacier change, and we need to have a robust understanding of how these landforms develop. Moraines can be removed by censoring processes such as the presence of ice within those landforms. So many moraines can be developed with an ice component, and as that ice melts out, the moraine structure and morphology can evolve. For example, I'd like to draw your attention to this diagram here. We can see that we've got an ice component within the landform, and we can see that our landform subsequently adjusts as that ice melts out, either by back wasting with ice-free cliffs, back wasting for ice-cored slopes, or by down wasting from the top. In many environments, such as in Iceland, these processes have been studied, and our understanding of the persistence of ice-cored landforms has benefited from these studies. You can see here on this diagram, for example, that we have ice cores reducing in thickness over time and sediment cover increasing. And this process, or the process in these temperate environments, can be quite rapid, and you can see the rates of degradation here expressed. The challenge is that in the high Arctic, some of these processes have not been or hadn't been explored in a great deal of detail. There's now a wide range of excellent studies starting to quantify rates of landform degradation in the high Arctic. Of course, understanding glacier change is underpinned by our ability to read that geomorphological or landform record of change. And so we need to understand some of these processes that impact those landforms upon deglaciation. For example, geochronological studies can greatly benefit from understanding some of the processes operating at modern or contemporary glacier margins. For example, cosmogenic nuclide exposure dating benefits from understanding where moraines may have undergone a period of degradation post deglaciation, because that will impact those exposure ages where boulders may be exhumed from the moraine. So of course, underpinning that is modern process studies, understanding these glaciers and how they deglaciate and how these landforms are responding to climate change. To provide the UK context, in the UK uplands associated with the Younger Dryas event, there are a wide range of hummocky landforms which have had a variety of hypotheses suggested for their formation over the time that they've been studied, whether that be ice stagnation, models associated with the active retreat of glaciers, and even models associated with the tectonic structure of glacier ice, or glaciotectonic structure of glacier ice, the englacial thrusting hypothesis. And key to understanding the dynamics or the former dynamics of these glaciers in the United Kingdom is understanding some of these processes and how they develop these landforms. So in the UK, for example, we have hummocky moraines like this, you can see on the chart. And controversial, or what has been a controversial hypothesis associated with the generation of these features is what you can see on the slide here, this englacial thrusting hypothesis, whereby longitudinal compression within glacier ice generates slices of, or elevates material into the glacier and isolates ice-cored elements, and these subsequently de-ice, generating these suggested englacial thrust moraines. However, this has been challenged in the literature and there's been lots of debate around it. And in the UK, there has been work seeking to draw analogues between modern day Svalbard and the Younger Dryas, and that again has been subject to debate in the literature. So a final idea about why it's valuable to look at this is that we now have a range of new techniques for understanding glacier change and the response of geomorphological environments to climate change. Here we can see a drone being deployed, and we can deploy techniques that we've used for a while in new contexts, such as ground penetrating radar, to start to understand landform evolution. I'm briefly going to talk to you about the study site we've looked at to evaluate landform evolution. We've looked at two glaciers in the Norwegian High Arctic, Midtre and Østre and they are valley glaciers that you can see here on the slide. These glaciers attained their neoglacial maximum extent in about 1890 AD and subsequently started to downwaste. Here you can see a 3D model of the glaciers produced from 1936 imagery, and the landforms we are interested in are these lateral frontal features that you can see adjoining the margins of these glaciers. And these glaciers have receded approximately 1,000 meters or a kilometer since attaining their near-glacial maximum extent. And again, you can see these near-glacial moraines. For this study, we focus on the true left moraine features of both glaciers to allow for comparison between adjacent sites to understand landform evolution. The methods we use for this approach combine two techniques: a geophysical approach using ground penetrating radar and geomorphologic change detection using raster differencing from multi-temporal digital elevation models. For the geophysical surveys, we deployed a pulse echo ground penetrating radar to sites in Svalbard, and we used two approaches. We use reflection surveys to look at the internal structure, and we use CMP surveys to determine the likely composition of the moraines, using the velocity of the radio waves propagate through that subsurface to infer moraine structure. For change detection, we used UAV surveys. We used the DJI S800 to obtain contemporary images of this landform, and we compare it to LiDAR data collected by the NERC ARSF and also photogrammetrically derived structural motion DEMs. And this approach uses spatially coincident cells to allow us to understand land surface change. And we performed this analysis using Wheaton and colleagues' GCD plugin. We use a minimum level of detection approach to account for uncertainty in these topographic data sets. I'm going to talk to you now briefly about some of the results that we've derived from these studies, combining the geophysical approach and the use of UAVs and high resolution topography. Here you can see Oosterlovenbreen, and we have studied Oosterlovenbreen, and we look at the outer lateral frontal moraine at this site, and we conducted a range of geophysical surveys. At this site, in lateral areas, you can see on these plots here that we have the velocity in meters per nanosecond and the two-way travel time. And we use CMP surveys to derive these plots. And the rate at which the radio waves propagate through the subsurface relates to that subsurface composition. So in this top plot, you'll notice we've got values clustering around 0.17, whereas on this lower plot that was derived from the frontal sections of the moraine, you can see we've got much lower velocities. We interpret these to indicate a ice-rich substrate in the lateral zone of these landforms and a debris-rich substrate in the frontal zones of these landforms. So we're starting to see some spatial variation in terms of the composition of these landforms. We may be able to use that to understand rates of de-icing across the landform assemblage. We also conducted these reflection surveys at multiple points across the landform. Here you can see one of the best examples from Oosterlovenbreen, a radar profile where you can see these very coherent up glacier dipping reflectors. And this is from a zone that we've derived velocities indicative of buried glacier ice. And so in this feature, we can see that these very coherent reflectors are probably indicative of ice and layering of debris within that ice. We do not see similar structures towards the front of the moraine. We see very chaotic radargrams derived from the frontal areas, indicative of a debris-rich composition with outsized clasts leading to chaotic returns. We then compared these data to our UAV survey, which looked at the 2003 to 2014 survey period. And this allowed us to link those radar data to rates of landform transformation to understand how there was an association between the subsurface composition and ice richness of that substrate and rates of landform transformation. And again, on this graph, there is a map. You can see very clear spatial variation in the rates of landform transformation across this feature. In the lateral zones, we see lowering up to 4 meters and exceeding minus 4 meters over the study period. But towards the front of the moraine, we see much lower rates of landform transformation at this site. So there's a really interesting spatial variation, which is again reflected in our radar data. We see those those ice-rich velocities derived from the lateral sections, and from the frontal sections we derive velocities more indicative of frozen diamicton. When we look at an adjacent glacier foreland, Mitra Löwenbräu, we see quite contrasting but very interesting results. At Mitra Löwenbräu, we again studied the true left of the glacier. Here is the feature we looked at on the previous slides, this ice-cored lateral frontal moraine. And here we can see the true left of Mitra Löwenbräu, and we are looking at, we surveyed an area using a UAV to obtain aerial photography, small format aerial photography, and we compared it to, again, GPR data. This panel here, you can see a true color image, a composite image of the survey area that was obtained with the UAV. The red dots here are our ground control points to ensure the quality of that topographic data product. And on this panel here, you can start to see some of the elevation data that we derive from this approach. We then compared this with LiDAR data derived from the NERC ARSF to allow us to understand changes over the decade. And these allow us to derive this digital elevation model of difference that you can see here. And we have buffered and removed data in excess of 100 meters from GCPs to avoid any spurious results. You can see at this feature that we have very high rates of landform transformation across the medial section of the moraine, and fairly moderate rates of landform transformation towards the frontal section of this feature. You may also recognize that we have debris remobilization on the lateral moraine slopes here. Again, when we use our geophysical instruments, we are able to determine an ice-rich composition here with a very thin veneer of sediment, whereas we have a debris-rich composition in this frontal section here. And again, if we start to look at and try to validate some of that data via walkover surveys, field surveys, we see features indicative of high rates of de-icing in areas where we derive those very high differences between the multi-temporal DEM data. Here we can see, for example, there are sections where we have exposed ice and debris flowage within this landform. And also we've noticed this ponding and lakes that have developed and the routing of drainage within this proglacial area by this ice-cored landform, which is key to understanding why rates of landform transformation are so rapid at this site. If we start to think about some of the comparisons with existing studies, start to think about some of the implications of this work, we have Östra Löwenbräu, a site where there is limited exposed ice, and downwastage appears to be the predominant process occurring, leading to more moderate rates of landform transformation. But we still have that spatially variable situation where there is more buried ice or higher ice content in the lateral sections compared to the frontal sections. At Mitra Löwenbräu, we have fluvial systems that make contact with and couple with our landforms, leading to high rates of landform degradation. And you can see in this table down at the bottom that the rates of change across different sites in a number of studies appear to be highly variable depending on the local topographic context. And there is now a wide range of studies that are starting to document this variability in terms of land surface evolution. So I'm just going to finish up with one final diagram. We've got our glacier here, nice conceptual diagram, moraine degradation occurring, with the rates being contingent on coupling with the fluvial system, but also contingent on the ice and debris content and the thickness of that overlying debris content, with the question whether higher preservation potential will be likely in areas that are debris rich. This study highlights the value of combining different approaches for understanding land surface evolution, combining that raster differencing and geophysical approach And we highlight that site-specific and local characteristics control the surface change on ice-core terrain in the high Arctic. Thank you very much for listening. And if you're interested in reading more, please see some of the papers listed on this final slide. If there are any questions, I'll be more than happy to take questions.